I want to welcome everybody in person and online to the 2022 season Pre Doc Symposium. I'm just going to say very briefly, just one congrats to the Pre Docs. It's been wonderful to have you involved in the community. You guys, is I think for everybody involved in the CCA an absolute highlight to have you involved in research here, and it's just it's delightful. I'm also really thrilled that those of you who were working remotely through the pandemic get to be here in person to share your work. I also do want to do a hearty thank to all of the mentors who have partnered with you on various projects, and also to Chris Hayward and the rest of the committee for their work in kind of shepherding this program along. I'm not going to take any more time. I'm going to pass off to Chris.
Thank you very much, Julianne. So yeah, I'll just reiterate Julianne's welcome and thanks to all of the pre-docs. Glad to have you here in person. And I've seen a lot of very interesting research that's come out of this. It's very exciting, and there's other research that I haven't learned about yet that I'm sure is also very exciting. So as you all know, we're going to have 10 plus 5 for talk plus question time. And we're going to do a break after Brent Tan, just take a quick 5-minute biology break. And unfortunately, I have to actually leave right now and go catch a plane in a few hours. So I'll be, listening in remotely as I can. But luckily, Matteo, who's currently on the committee, and Simone, who was previously on the committee, they've offered to take over and run things. So Matteo is going to handle the first half here.
Right, that's great. So as I said to Simone, let the Italian take over. So my job is going to be to keep this on time. And so we're going to start with Alex Galliano, and then we're going to have Ankita Bear on deck. As Chris mentioned, 10 minutes plus 5 per question. You can eat into the question time, but I'll try to keep you straight to the 15 minutes. And at the end, I will hand you your certificate. So.
Hello, everyone. Thank you so much for being here today. I'm Alex Galliano. I'm entering the final year of a graduate program at the University of Illinois at Urbana-Champaign. I'm also entering my final week of a pre-doc program here at CCA. Probably will not come as a surprise to all of you here. And today I'm going to be talking about the work that I've been doing this semester with Dan and Gabby and a bunch of other people to use host galaxies to improve real-time transient classification. And I'll try and break down each of those pieces of that title and exactly why they're valuable. So historically, spectroscopy has been kind of the bread and butter of supernova studies. If you want to connect the phenomenology that we observe to the underlying physics of what's going on in the explosion and try to derive some meaning about a progenitor star that exploded in this brilliant event, you need spectroscopy. The problem is that our discovery rates over the past few years have really exploded. They're breaking exponential scaling, and our spectroscopic resources have not increased to be able to match that. And to make that point a little bit more visceral, I've made this movie of the number of explosions that we've seen that we either have spectra for or don't have spectra for since the year 1800. And you can see, unsurprisingly, early on, we find a few events, we get spectra for them, we're doing pretty well. Eventually, let's say the 90s, CCD technology takes off, synoptic surveys start to become possible, and now we see that the sky is fully covered in these explosions. We now believe that there is one supernova happening every second within a redshift of 1. And the real challenge of our field now is to try and figure out how to very quickly determine from the light curves, from the photometry that we observe from these events, which ones are interesting, and to allow us to go get targeted spectroscopic follow-up of a few interesting ones from out of this massive pile of things that we're finding. Okay. So the reason we want to do this quickly is because now our technological capabilities are pushing us towards the discovery of things happening on faster and fainter timescales than ever before. Here's a parameter plot vertical axis is brightness, horizontal axis is characteristic decay timescale. We're already finding a couple of these events that are really fast, we don't know much about, so we've named them phenomenologically with things like FBOTs, FELTs, RETs, ILOTs, tons of different acronyms right now in the transient zoo. But I want to make the point that not only are we going to find unique classes of transients with upcoming surveys, but we're going to find unique phenomena and physics happening with classes we already know reasonably well. And a lot of that happens in the first couple of days of the explosion. So I'm just highlighting 4 different phenomena we can see here that are encoded into the first few days of transient light curve that say something about the progenitor system or about the surrounding environment that the explosion interacts with as it explodes, okay? So the landscape for being able to do this, for typing supernovae with photometry alone quickly, has typically looked something like this. I'm sorry, this is a very messy plot. That is the purpose of this plot. Within the past couple of years, a lot of models have been developed that are incredibly complex, and they've been constructed to be complex in order to bridge the gap between simulations and observations. This is historically a really hard thing to do, but the increased model complexity comes at the cost of interpretability. So here are 2 models that I'm highlighting. One is this one right here, which was made in 2021. The other one is this attention network top right. And so when developing this project with my collaborators here, the philosophy at the heart of our project was, how do we better bridge the gap between simulations and observations of transient light curves without increasing model complexity that we can't justify? And one of the ways that we can do that is by making our simulations more realistic. It turns out that for decades, we've known that the type of a transient is correlated with the local environment around that transient and the galaxy that it occurs in. And this kind of makes sense. If you think of a galaxy as just a population of stars, then on average, if you find a galaxy that has lots of young stars, then an explosion of a young star is more likely to happen in that galaxy. And so earlier this year, I and a few colleagues developed this massive simulation called Scotch, which is a database containing 5 million different simulated transients as we think LSST will see them, including the host galaxy information of those transients, as well as we can determine them from past studies. So this forms the main framework, the main data set that we worked to characterize using our project. And the main framework, the main architecture that we used for our model is a recurrent neural network with 1 layer. Okay, so all of the different pieces that I showed on the earlier slide, this is 1 layer of a recurrent neural network. I don't have a lot of time to go into the details of what a recurrent neural network is, except to say that it's composed of individual units that take in information as a flow from previous time steps to later time steps, which allows you to make predictions in real time. So the hope, if you've trained your network well, is that at early times, you're able to make a prediction, maybe it's okay, it's decent, but over time, as you get more and more photometry in from this event, then at later times, now you're doing much better at classifying this supernova. The problem is, with a lot of neural networks, you have to evaluate the light curves that you're interested in characterizing onto a common grid. So the way that this is typically done is you would either pad the light curves onto a fixed length grid, or you would interpolate your observations. We chose the interpolation route, and we did this, of course, working with Dan using Gaussian processes. And Dan has developed a Gaussian process model that is pretty nifty. It is parameterized by the correlation between observations in both wavelength space and in the time direction. And this is awesome because if you have a model for a light curve in one band and you get observations in another band, this improves your model fit across all bands. So to kind of show how this works in practice, I'm showing top right a video of a Gaussian process fit over time as you get more observations in. And you see eventually at 200 days after discovery, you have a pretty reasonable characterized light curve from your observations that you can then use to interpolate and pass into your network. And I should mention that there are a couple science groups that are already interested in using this for their own science goals. Okay, so initial results on the simulated data. On the right, I'm showing the classification probability as a function of the number of days since the event was discovered. And on the top, I'm showing the simulated photometry from the event. And on the left, I'm comparing it to basically a similar plot from an earlier model developed in 2019 by Daniel Muthukrishna. So if I play the movie forward, you see that over time, you get a spike in the classification probability of the event being a type 1a supernova, and you have almost zero probability of being anything before you've discovered it because you have no prior information. And on the right, I'm showing this same plot, not in real time, but you can now see that we have a classification probability of the event being a type 1a supernova before trigger, before you have any real detections from the light curve itself. And then once you actually have real detections from the photometry, the classification probability spikes up and it says, okay, now I'm really sure that we're looking at a type 1a supernova. Now, I talked a little bit about bridging that gap between simulation and observation. One of the ways we did this was by making our simulations more realistic. But there are lots of different pieces that we added in along the way, a lot of different insights that were gained to actually be able to bridge that gap. One of them was a piece of transfer learning, whereby we take our model, we train it for the vast majority of the time on simulated data, and then we tacked on a little piece of training at the end on real observed data. The hope is that this can tweak and pull the weights of the model in different directions to better transfer from the simulated to the observed data set. We also added in this Gaussian scatter to our simulated photometric redshifts because our model was pretty dependent on redshift information. And then the last piece was we determined a loss function, a custom loss function that counteracted the fact that you have a very imbalanced real data set and we don't want to throw out any of that data. So we counteracted that with a loss function that takes that into account. And taking into consideration all of these pieces, this is our performance on real data. So on the left are our results. On the right is a classifier called parsnip. That was that kind of snaking architecture that I showed you in an earlier slide. And this is a confusion matrix, okay? So the classification accuracies of each of the classes are shown along the diagonal. And this is the same data set applied using each of those given architectures. And essentially what we find is that our classification accuracies for each of the three classes that we're predicting on in the real spectroscopic sample of supernovae, our performance is comparable between the parsnip, the much more complicated model, and our network using one single RNN layer. And so the takeaway here is that by pushing really hard to try and mitigate those factors that differentiate simulation and observation, we can achieve comparable performance on real data to a lot more complex models. And the hope is that this model will be a lot more interpretable as well. Okay, so conclusions. I think that host galaxies are a vastly underutilized resource for transient classification. To really see what the network is learning, we want to play around with, there's a thing that I found recently called Shapley values that we're hoping to integrate into our network to be able to interpret how important each of the features are in classifying these and to see exactly how much this host galaxy information is actually valued here. And we want to push out to early classification. We want to see how well we can do early on in the light curve when you don't have much information yet, but you do have all this host galaxy information that can tell you something. There are also well-known host galaxy correlations for rarer classes of events like tidal disruption events and superluminous supernovae. And the hope is that when we classify on those, we'll see even better performance. And then we want to actually put it in practice. So I'm part of the Young Supernova Experiment, a massive collaboration that has this as its primary goal. And the hope is that once we get this up and running for multiple different classes, instead of just the 3 that I showed on the previous slide, we can actually put this in place and start finding interesting things early. So I'll end there. Thank you so much to Simons Foundation. Thank you so much to CCA for having us over the past 5 months. It's been an incredible program, and I really appreciated all the conversations I've had during my time here. Thanks, and I'll take any questions.
Thanks so much, Alex. So it's time for questions. We have a couple of minutes. If you ask a question, please use the mic, which is on your chair.
I'm gonna have to say this after everyone, but super awesome, amazing that this is 5 months of work. Anyway, maybe I missed this, but what about the host galaxies are you actually using? Is it just the integrated photometry, or is it shape and morphological things?
Yeah, that's a phenomenal question. So when we started, let's see, maybe I went back too far. When we initially did this, just to see the value, we used derived properties. So we use star formation rate and stellar mass from the simulations. But because we want to apply it in real time to real data, when we actually put this in practice, we use GRIZ broadband photometry. But the question is going to be, to what extent can you estimate some derived parameters in real time? And will that give you better prediction accuracies? Still thinking about it.
More questions for Alex? So maybe I'm going to ask something. So this is obviously amazing work, and I'm interested a little bit in this classification method you use in models. So what happens if you have like and this is going to happen, it's going to be like a transient that you haven't seen before, and how this classification algorithm respond to that? Have you tried to injecting some weird light curve on across different wavelengths?
Yeah, we have not. The simulations in Scotch were trying to integrate all of the correlations between transient and host that we know about, but the simulation framework is all in place, and we are thinking about what it might look like if we put in either a weird transient light curve with no correlation with their host environment, or a weird transient with a very strong correlation that we've never seen before, and to be able to pass that through. And I hope that that if you train it well, it'll be flexible to that, but we'll just have to see. Thanks.
Great. It's funny when you said this alarm, you never know what kind of a sound will come out, but you can bet it's going to be an annoying one. So that worked with this job. Okay, cool. Alex, thanks so much again. So we have now Ankita Bera, and Antonio Porras is on deck. Oh, wait, sorry. I forgot the most important part, which is this is your certificate of completion for the Pre Doc program at CCA. Congratulations. Thank you.
Hello, everyone. I'm Ankita Bera. I'm a grad student at Presidency University. It's in India. And this work I'm doing in collaboration with Sultan Hassan. So this is the entire picture of the evolution of our universe. Now, there are different phases for different evolution, but we are mostly interested in these 2 periods, the cosmic dawn and the reionization. Now, let me briefly explain these periods. So in terms of these absorption and the emission signals, so these with the formation of the first stars or the first generation of galaxies, the universe enters this period called the cosmic dawn. And then the Lyman alpha photons from these fast stars, they actually alters the spin states of the ground state hydrogen. And then we get this absorption profile of the cosmic dawn, which is the 21 centimeter absorption profile. Now, as soon as the heating sources started to form, it heats the ambient gas in the intergalactic medium, and then the absorption profile goes to the heating. And then the ionizing photons from these fast stars, they start to ionize the intergalactic medium, and this deionization continues till there is some neutral hydrogen left. Now, I'll use this terminology, this cosmic dawn period, as high redshift and the end of reionization as low redshift. Now, currently, we have only one observation at this cosmic dawn period, and that is this AGES observation. Now, it is based in Western Australia, and they have their two instruments for different redshifts. And on the upper hand side, it's their total detection, which contains the foreground, the signal, and the systematic. And then they extracted the 21 centimeter absorption signal from these total signal, and this is their best fit profile of the 21 centimeter profile. Now, this is interesting because the absorption depth of these profile, it is almost 2 times larger than the standard strongest prediction. So, which creates a debate and a discussion in the community. But assuming this fact that this detection is correct, we'll move forward. And then after this detection, in Madal 2018 paper, we have shown that these AGES detection could be converted to the star formation, then density, or the UV luminosity. Now, if we look at the high redshift measurements, it's actually going down, but only if we linearly extrapolate the UV luminosity function, then it fits with the AGES detection. So from here, we are taking our high redshift measurements, that is measurement from the cosmic dawn. And then along with that, we are taking some post-reionization measurements. First one is the reionization history. Now this is a volume average neutral hydrogen fraction of the intergalactic medium. And this is the evolution with the redshift. Now there are different sets of observations from the Lyman alpha 40s, 7 big galaxies, USOs, etc., etc. And then along with that, we are taking the optical depth, the Thomson scattering. This is the evolution of the Thomson scattering optical depth. And the red dashed one is the measured Planck value. So with that, we are also taking the ionizing emissivity. This is the integrated emissivity of the ionizing photons. And this is also a function of redshift. So now we have all the measurements from the cosmic dawn, that is from high redshift, and from the post-reionization, that is from low redshift. Then we are taking our source model like this, and this is driven by the radiative transfer simulation. Now, this function, it takes care of the non-linearity of the halo mass, and it has a shape of the, it is quite analogous to the sector function, which has a power law cutoff on one end and the exponential cutoff on another end, which will be clearer from these two plots. Now here we have plotted this function, keeping the parameter C being fixed. And from here we can see for different B, this B parameter is basically parameterizing the exponential cutoff of this function. But the most interesting parameter is this C parameter, because if we fix B and if we take positive C, then it has a tendency to include more massive halos, because it's the power dependence of the halo mass function it's defining. So, and if we take the negative C, then it has a tendency to push towards these low mass halos. Now, these parameters will help to shape our results later on. And then now, first we are taking the star formation history, that is the high redshift measurement, and then we are taking our source model. Here, all these quantities are globally or average quantities. So we are taking the semi-analytical approach. We are applying MCMC, the MC which is available in Python. And now this is the constraints that we are getting. Now let me explain these constraints in a more detail. This green one is if we restrict our analysis to redshift greater than 16. And the red one is if we restrict our analysis for redshift less than 10. And then if we take the entire redshift from redshift 5 to 20, then we get these blue contours. Now, this B parameter, it has a tendency to take the value like 7 or 8, which is quite similar to the simulation. But this C parameter here, from here it is clear that if we take only the high redshift measurement, then it has more tendency to go to the negative side, which means it requires the contribution from the low mass halos. Whereas if we take the measurements from low redshift only, which is the red one, then it has a tendency to include more massive halos. And if we take the entire redshift, then it becomes in between of these. Now to cross-check our model, we these inferred parameters, we use these inferred parameters to check if our model is working perfectly or not. And then from here we can see that it's within the 1 sigma level. So from here we can say that our model is working quite well. So then we are taking then in our likelihood calculation, first we are taking the reionization history, the optical depth, and the ionizing emissivity. And for that we are getting these red contours or the red constraints here on F escape and the C parameters. Now first we have taken all the parameters, we varied all the parameters, but we check these A and D. What values we are getting, it's quite similar to the simulation. That's why we have fixed A and D. And then as B is the exponential cutoff, and that is 7 or 8 in each cases. So that's why then we fixed B as well. And we only varied F escape and the C here. And first, when we take only the low redshift measurements like the reionization history and the optical depth and the ionizing emissivity, then we are getting very low F escape and quite positive C. Whereas after that, we are taking the star formation with it. And if we take the star formation, that is the high redshift measurement, along with this low redshift measurement to check what conditions we require to bridge the gap between these measurements, then we find that these if script has a tendency to push things towards on the higher side. That means if we need to bridge the gap, we need higher if script. For high redshift, we need more number of photons to be escaped. And if we see the C value here, then for including the star formation, it's going towards negative side, which means the low mass halos are required to bridge the gap. So with this, let me summarize briefly what we have done. We have taken measurements from high redshift that is motivated by edges, and then these edges measurements, we are taking the star formation, and that star formation is converted to the UV luminosity density. And then along with that, we are taking some low redshift measurements, which are reionization history, ionizing emissivity, and the blank optical depth. And what we have seen is if we need to reproduce the high redshift measurement, then we need the contribution from low mass halos. Whereas if we take the only the low redshift measurement, then the massive halos are more important. And to bridge the gap between these two, we need a very high fraction of photons to be escaped. So with this, I end here, and I would like to thank Simons Foundation for giving me this opportunity, and also the XACD and the CCA cluster that I used for these. So yes, thank you.
Thank you so much. Thanks, Ankita. Time for questions. Julianne.
No, thank you so much for that. I'm wondering, like a lot of these quantities are things that probably do evolve with redshift, like you would expect the escape fraction to not necessarily be the same at different redshifts. Do you think there's enough information to extend your model to include, like rather than one value that works over this whole redshift range, but to allow some evolution in some of these quantities?
Yes, we are actually thinking to include the evolution of the F escape, that if we include the evolution of the F escape or with the halo mass function and also with the redshift, it might get changes. That's why it's not the final one. So we are actually currently working on that to check that. Yes, that's perfect.
More questions for Ankita? Yeah. Adrian?
Thanks for that talk. That was great. So have you thought about what the implied star formation rate per low mass halo would be required to provide enough to explain the edges signal? You know, like if you combine the star formation rate measurement with this, can you then estimate or predict what the star formation rate per low mass halo would be?
So if I understand correctly, we are considering the halo masses from very low, like from 10 to the power 5 to 10 to the power 14. So, so we are checking that if there is any dependencies on these halo mass function, like if we take very low mass halos and very high mass halos, if there is any dependency, so we are checking that. We have taken very high range of these halo mass function. I don't know if you are asking this.
Wasn't what I was asking, but that is useful to know. But I'll ask you later on.
Oh, okay, sure. Thank you.
Okay. So if there are no more questions, let's thank Ankita again. My great pleasure to hand you in your certificate of completion for the Pre Doc program. And congratulations. Right, we have Antonio, and then we have Arvind Gupta on deck. Okay. Perfect. This is for you. Great. All right, Antonio, take it away.
Okay, thank you. So, hi everyone. I'm Antonio Porras. I'm a PhD candidate at Vanderbilt University, and I'll be presenting work with John Forbes, Rachel Somerville, and Shai Ganel. But I want to tell you 3 facts that makes me a scientist right now, because I think that's important. One of them, I'm from Costa Rica. 2 of them, I'm a FIS Vanderbilt Bridge Fellow. And if you don't know about that, you should definitely talk to me about it. And I'm also the president of the Central American Caribbean Bridge in Astrophysics, which is a nonprofit organization created to expand and create astronomy research opportunities in Central America and the Caribbean. So with that in mind, I'll tell you about the scatter and the stellar mass within the stellar mass to halo mass relation. So first, we know observationally there's not many very massive stars in the real universe. We know that we need feedback mechanisms to suppress star formation so that the simulations can then look like what observations may look like when they match stellar masses with dark matter halos. And so this is just to indicate the importance of feedback overall in the whole galaxy evolution framework. And when we look at how empirical models use this relation, they basically look at the stellar mass of galaxies and match them with dark matter only simulations. And there's different ways of matching these halos. There's definitely different methods, but the important part is that these empirical methods are used by many hydrodynamical simulations to match their mean or median stellar mass to halo mass relation. So in other words, hydrodynamical simulations use these empirical relations to calibrate or to fit their stellar mass to halo mass relations. And but what they don't fit is the scatter within the stellar mass to halo mass relation. So the scatter and stellar mass. So the scatter and stellar mass within the stellar mass to halo mass relation is a true prediction from the physical models. And so on the right-hand side is what I'm really interested in, which is on the y-axis is the scatter and stellar mass as a function of halo mass. And what I'm really curious to know is why is it that hydrodynamical simulations all agree with one another, but they disagree with semi-analytic models, which they all agree with each other, but they also disagree with empirical models, and empirical models also disagree. So this is like a whole mess. So this is what I'm really curious to know. So hydrodynamical simulations, which you find in the dotted line, they all agree with one another in that the scatter in stellar mass is constrained to be less than 0.2, and it kind of spikes up as you go in lower halo masses. They all agree with two, Becker and Eyring and Watson's empirical models. And then SAM's, they all agree with one another that the scatter is actually much larger. And they also have somewhat of an agreement with the universe machine from Baruzzi 2019. And so the idea is that I would like to use derivation of SAGE. There is another one called dark SAGE. I don't know why it's dark, but it's different. And the goal is to use dark SAGE to try to understand what creates the large scatter in the semi-analytic model. Hopefully, in the near future, try to understand whether or not the scatter is common amongst all the semi-analytic models, exactly what is creating such a large scatter. And so very briefly, the reason why I use dark SAGE is because I like how it evolves the disk structures. It does something different than many other semi-analytic models in that it treats every disk as a set of annuli, and within those annuli you have a fixed angular momentum measurement, and within that you basically have many physical properties that allows the galaxy to be more better resolved than the other semi-analytic models. And so, sorry, how do I fix it? Okay, I guess I'll go through all that. And so yes. And so creating a very simple experiment. Actually, I think I skipped one. So when we look at the semi-analytic model dark SAGE and TNG, you know, it is no surprise that dark SAGE has a large scatter in stellar mass at fixed halo mass for most of the halo masses, and TNG has a lower scalar mass. So this is very similar to what we have seen before. This agreement that SAMs usually have a larger stellar mass scatter. And so the idea now is, can we run some experiments to understand what's causing this large scatter? And so a very simple experiment, which was just turning off what we call the radio mode feedback in the SAM universe. And what the radio mode feedback is basically means is just dumping a lot of kinetic energy into the hot halo so that it prevents the hot gas from cooling. When you turn off that mode, you basically get rid of all the scatter in dark SAGE, and that's on the right-hand side panel. Dark SAGE is the purple line, and when you turn off that mode, you get rid of all the scatter. So this is really impressive, but then we get the problem that all galaxies at all halo masses have larger stellar masses. So we don't want that. We definitely want it to look like TNG to really understand what are the processes that contribute to the scatter. But this is really interesting that at least from the radio mode, we're able to understand that the scatter is contributing a lot to the that the radio mode is contributing a lot to the scatter in stellar mass. And so what we did was try to understand the contribution of the black hole itself. And here is this stellar mass to halo mass relation colored by the quench fraction for dark SAGE on the left and for TNG on the right. And what we find is both of the models have a very different ways of quenching in terms of in TNG, you see a very sharp transition where everything above some stellar mass is quenched. And that is very highly tied to the black hole mass and how feedback is also implemented in TNG. Whereas dark SAGE is just a whole mess. This is what people would call the hybrid quenching model where they say that the stellar mass and the halo mass are contributing to the quenching of galaxies, whereas in TNG is more so the stellar mass. But this is just to show that there is some key interesting feature that we can see in TNG that we can try to implement in Dark Sage and see whether or not we can control for the scattering stellar mass. And so what we did was, well, we start with the black hole. We know that here is the black hole mass as a function of halo mass. The mid panel is an experiment we did, which was basically looking at the seeding of black holes to make it look like TNG, because the thing is that the seeding in Dark Sage is very different than TNG. We have that in Dark Sage, black holes start from mass of 0 and they evolve all the way to 10 to the 9. Whereas in TNG, they basically seed a black hole of 10 to the 6 in halos of 10 to the 10.5. And so we wanted to make the seeding to be like TNG in Dark Sage to see whether or not the scattering stellar mass would change. Turns out it doesn't do much. And so what we did was we took the black hole mass, halo mass median relation in TNG, and we forced Dark Sage galaxies to follow that relation. So we took out all the evolution of black holes in Dark Sage, and we just forced all black holes to have this median relation like in TNG. And besides that, we also have this, what we call an input parameter, which basically we tell the scatter within the black hole mass halo mass relation what scatter we want. And so that's what we're going to be controlling to see how we can change the scattering stellar mass. And this is just the main plot. And basically, what we see on the y-axis is the stellar mass scatter. On the x-axis is the black hole mass scatter. That's what we're able to control. And what we find is that, the different lines are different halo mass bins. So the boldest colors are the higher halo mass bins. And then the black dashed line is the one-to-one line. So again, we have different runs of the model for different scatters in black hole mass halo mass relation. So we have a scatter of 0, so no scatter, 0.2, 0.4, 0.7, and 1. And we find that for the highest mass halos, it doesn't really matter what scattering black hole mass we choose. The scattering stellar mass becomes constant, so it doesn't really change much. But around the quenching mass and below, it does play a significant role to change the scattering black hole mass. And we're able to get it down to 0.1, and when before it used to be pretty high. So that's an interesting result, because we're able to get it as low for some of these halo mass bins. We're able to get it as low as TNG scatter. However, for the higher halo mass bins, we aren't able to do that yet, and we have some ideas as to why that's the case. But you can ask me about it because I don't have time. So just in summary, I would like to point out that doing a very simple experiment like turning off the radio mode feedback decreases the scatter significantly for the Similic model Dark Sage. Be interesting to see if in other Similic models that would be the case. Well, we know from the clue that in TNG, the transition of all galaxies being quenched above some stellar mass or above some black hole mass, from that clue, then we're able to understand that the black hole mass is also contributing to the scatter if we are able to control it. And we were able to show that that's the case for galaxies, at least for Dark Sage, for galaxies around the quenching mass and below, we're able to control for the black hole mass. That by controlling the black hole mass in the scattering black hole mass, we're able to also control for the scattering stellar mass. I don't know, that's a lot of words. It was clear to me. I don't know if it's clear for you. So you can ask me about it more. But yes, so I'll stop here. And I would like to also thank Rachel and John Forbes, Shai Ganel, and the Flatiron Institute for giving me the opportunity to do this, because it was a lot of fun. So thank you.
Thank you, Antonio. Questions? Yes, Sultan.
for the talk. So this is a topic very close to my heart. So we know also, like for the scatter in like the scatter due to stellar feedback, we know also you can expect a scatter when including like for contribution from the merger history. So if you have merger, right, you add mass to the system and that adds more scatter. So did you look at that?
Right. Yeah, that's a great point, and we do believe that there's a contribution of the scattering stellar mass for the higher mass end due to mergers. We didn't look into it in terms of like, I guess, physically speaking from the model, but that's our one of our ideas that's contributing to the high scattering, the high halo mass spins. Yeah.
Okay, another quick question is that did you look at the duty cycle for
The what?
the duty cycle?
We have not looked.
Okay, all right, thanks.
More questions? Actually, I was actually interested in knowing more about the Chanka Bridge, since you mentioned it quickly at the beginning, so I knew part of it. So can you tell us a bit more?
Yes. So it's okay. So since 2016, we have gathered people to come give talks to this is all virtually to I guess seek representation of Central American Caribbean astronomers and work with undergrad students. We have a remote internship where we pair students from undergrad institutions in Central America and the Caribbean with US or Mexico, Brazil, China, different institutions to do like a 4th-month remote internship program. This past December, we were awarded 21,000 euros to pay the students and to conduct other objectives. And we just filed as a nonprofit, and so that's very exciting. So next goals is definitely try to get more support for it. But yes, that's very quick. Yeah.
That's super interesting. Yeah. Okay. We have no more questions. Let's thank Antonio again. And it's a great pleasure to hand you your certificate of completion for the CCA Pre Doc. Do you want me to take a picture?
I was gonna take a selfie.
There you go. Awesome.
Awesome. Thank you.
Thank you. Next is Arvind Gupta, and on deck is Avinash Chaturvedi.
Yeah. Thank you. So this just goes forward back. Pointer. Yes, it works.
Perfect. All right, take it away.
Okay. Thank you, Matteo. So my name is Arvind Gupta. I'm a PhD student at Penn State currently, and I've been working for the last almost a year now remotely with Megan Bedell, as well as collaborating a little bit with David Hogg and Dan Foreman-Mackey, as well as some others who are not at the CCA on a project to study the Fisher information content of extreme precision radial velocity exoplanet surveys. And today is not June 22nd. I have the wrong date, but the rest of the slides are good, I think. So to start out, so there are a handful of ongoing and in the works extreme precision radial velocity exoplanet surveys. 2 of these are the NUID Earth Twin Survey, which is a survey I am heavily involved in through my work at Penn State, and the Terra hunting experiment, which is something that many folks here at the CCA are involved with. Both of these are surveys using high precision spectrographs, so spectrographs that can achieve instrumental precisions of under a meter per second to stare at some number of dozens of stars for 5 years in our case, 10 years in the Terra hunting case, to look for nominally Earth analog exoplanets orbiting stars like the sun. So these are planets with radial velocity amplitudes of about 10 centimeters per second, periods of 300 or so days. And then also some secondary goals of these surveys are to get better constraints on occurrence rates down to this limit. So when designing a survey like this, there's a lot of decisions that need to go in. You need to choose your stellar target sample, how many stars you'll observe, what types of stars to observe, the number of observations per target, how those observations will be distributed. And in many cases, when tweaking just a single parameter, it's pretty easy to tell how that tweak will affect your success metrics. So whether or not you can achieve the metrics you're going out for. If we increase the number of observations per target, we'll get better precision, find more Earth analogs ideally, and things like that. But none of these changes can happen in a vacuum. Everything has some sort of trade-off. If we increase the number of observations per target, we will have to decrease the number of targets or decrease the precision with which each of those observations is conducted. And in doing this, we want to find a way to take all of the time we have allocated, design a survey that balances all of these different decisions to ideally optimize our success metrics. We want to strike some really good balance there. But it's not always easy to figure out where that balance is, or which of these different parameters are the most important in optimizing those success metrics. So to figure out where that balance is, one way that traditionally radial velocity surveys have tried to characterize their precisions is through injection recovery tests. So these are tests where observers will conduct a survey or simulate a survey, take all their observations, inject exoplanet signals, and then try to fit those out to figure out where they'll actually be able to recover the injected signals and where they won't, to find out what their sensitivity limits are, find out what they could have detected. These are great, but they are often very computationally expensive for reasons that I won't get into here. And more importantly, the recovery rate that you achieve is strongly model dependent. So we're not just fitting pure Keplerians to find exoplanets in the data. We also have to add Gaussian processes and things to account for stellar variability. And the detection techniques that we apply right now when we're running these tests to simulate surveys probably won't be the same as the techniques we use a decade from now, when hopefully things will have improved. So we don't want to just simulate our full survey and then predict what our results will be when we're not using the same techniques we'll actually use when we have the data in hand. An alternative approach here is to use the Fisher information content of each survey. So the Fisher information, in short, is something that tells us the uncertainties on a set of model parameters given some corresponding set of data. So if we have a sinusoidal radial velocity signal model and some set of observations for that model, then the Fisher information will tell us the uncertainty on the semi-amplitude, period, and phase for some set of parameters. And this is useful because the Fisher information calculation requires us only to simulate the set of observation times for the survey and to have a good understanding of our noise model or our covariance matrix. This makes it a lot more efficient than injection recovery tests, and it makes us a little bit more agnostic to our specific model, or at least flexible in changing up that model and resimulating the survey without too much additional computational expense. So for the Fisher information of a radial velocity survey, we have to consider two different categories of noise. There's white noise. This is just something like photon noise, which does not have any covariance between observations. And then correlated noise, predominantly stellar variability, where we actually expect pairs of observations to be correlated with each other in the signals that we observe. I'm not going to get too much into the white noise here. This is something that we might not actually even need simulations to fully understand. But the correlated noise, which is what we're more interested in, is what I'll talk about. So on short timescales of less than a night or so, there's two main sources of stellar variability which contribute to our signals. These are stellar P-mode oscillations and surface granulation. And these plots here are showing the covariances between pairs of observations for as a function of different separations between those observations. And you can see that these are timescales of both of these are to about 30 minutes or so, which means that if we are conducting a set of observations within a single night, we expect that the precision that we achieve will depend on how exactly those observations are distributed, because that will change which covariances we actually end up observing. So I ran some unit tests, and we see that that is precisely true. So these tests, the 4 different lines here, are simulating 4 different strategies of simulating observations within a single night. If we take 100 nights of observations and take 6 observations per night, but distribute those differently within each night, we get these 4 different curves. And this is from uniformly distributed across the, where is my pointer? Okay, uniformly distributed across the night out to all concentrated together at one point in the night. And we can see that for oscillations, for example, we get the most Fisher information, the highest precision, when we cluster all our observations together. This makes sense for folks who are familiar with how exactly the covariance of p-mode oscillations works. For granulation, we see the opposite result, where if we spread our observations out, we end up getting more Fisher information and higher precisions. These are at odds with each other. One of them suggests that we should concentrate our observations together. The other suggests we should spread them apart. If we put them together, we see that the exact preferred strategy will depend on how much time we're willing to dedicate to each target on a single night. So that's what the x-axis is here. This is the amount of time we spend on a night on each of these targets. But this works pretty well. It tells us exactly what we're looking for from a Fisher information perspective. And for the specific kernels I used, it gives us concrete results. We can vary those kernels, update them as we improve our understanding of each of these sources of variability. But this is a pretty promising result in that it shows us what we want to know. On longer timescales, so timescales of many nights, a different source of noise is more important here. And this is stellar RV variations that are induced by activity. So sunspot or star spots on magnetic fields. And we can see that here, the this like doesn't point where I expect it to. There we go. Okay. The x-axis is now in days instead of minutes or hours, which means that if we take observations distributed across a year and change how that distribution works, then that changing distribution will affect the precision that we achieve with this type of noise in our covariance matrix. So I tested out a handful of different strategies. There's a legend here that is probably a bit too confusing, but I'm going to highlight a few of them. So you have the purple one that's second from the top on the right, which gives us the worst Fisher information here. And that is if we were to distribute our observations in a set of discrete clusters over the course of the year, that performs a lot worse than the gray one, for example, at the top, which is concentrating all of the observations together. This is not quite an expected result, but I will caution that it is very model dependent. So if we use a different kernel for what we expect the activity to look like, we might not get the same result. But this is showing at least that we can distinguish between the success of different strategies for any given model for our stellar activity. Another thing I'll point out is that I'm using a period of 300 days here. If we're looking for a true Earth analog, we'd be looking at the Sun-like star and looking for 365 days. If we change this from 300 to 365, the structure actually changes quite a bit. And this is because we have to deal with practical constraints as well. We can't just observe whenever we want to. Stars are only observable for a finite amount of time over the course of the year. In this case, I'm using an 8-month baseline. That's pretty typical for a star from a mid-latitude. And we can see that now this strategy where we concentrate all our observations together, that's the gray one, starts to perform a lot worse at low numbers of observations. And that's because we're only sampling a very small part of the phase of that planet now. Because of 365-day period and fixed observing seasons, we're not getting the full distribution of phases. So we're focusing a bit more on this case of 300 days because that's a bit more typical than looking for an exact true Earth analog. But it is important to note that if we're looking for something just like the Earth, we do have to consider a few different things, which flows into the final piece here. So all these tests I showed so far use an idealized observing schedule where we assume we can observe exactly when we want to over all times of the year for just a single star. This isn't going to be the case in practice. Most stars aren't observable year-round. Sure, there's some that are circumpolar. We can never observe 2 stars at the same time, at least with current spectrographs, mostly single fiber spectrographs. Telescopes and instruments need maintenance. They aren't on sky every single night of the year. Weather is unpredictable. Even if we develop a full observing schedule based on when we know the telescope's going to be up and the stars are going to be up, the weather can mess things up too. And as I learned last week, your observatory can sometimes catch fire. So yeah, that's fun. But we can also develop a tool that accounts for all of these things and accounts for the observing constraints or the idealized cadence that we want to use, in addition to these constraints, to build an observing schedule that simulates a complete survey from which we can calculate the Fisher information. So we have a tool that can do this now. This is a 1-year simulated survey for a set of 30 stars with realistic constraints on when we can observe, some probabilistic constraints for weather, things like that. And from this, we can develop an observing schedule and then calculate the Fisher information, figure out the best strategy to use. Unfortunately, haven't done that yet. That is part of our future work here. But we do have all of the pieces in place. All that remains to do is put it together and figure out what the ideal strategies are for future EPRV surveys. So with that, I will take questions.
Thanks, Erwin. Questions? Dan.
This is awesome. So you talked about how you can change the model for the stellar variability. Are you also using the requirement that you can perfectly know the covariance structure of the stellar variability or something too? Is that also baked in currently?
That is what the Fisher information implicitly assumes, I think. Yeah. Is that we are the model we put in there is the actual true model of the star's stellar variability. Yeah.
Good. How feasible do you think that is?
Oh. I don't know how feasible that is. The models that we're using right now are all based on the sun, where we have extremely high cadence observations over many years. So for real stars that are different from the sun, I would guess that we do have to incorporate. There's a term we can add to the Fisher covariance matrix that accounts for the uncertainties on the parameters of the noise model too. So, yeah.
Yes.
I like audibly oohed and awed during your talk. So from your simulations, what would you say is the parameter to tune that most affects the success metric that you get at the end?
That most affects the success metric. It seems that it's going to be observing the cadence. It's the cadence of observations across many nights. Within a single night, that's the part that is with respect to oscillations and granulation. Maybe that one matters a lot, but that's something that we kind of already knew, that we want to concentrate things, get long baselines for oscillations. But the cadence across many nights seems to be the sort of newer result. What we've seen so far from our results is counter to some common knowledge of what people think is the best strategy. So I think that's going to be it.
Yeah. Awesome, thanks.
Okay, well, let's thank Arvin again. Wait, where are you going? Come here. Let's pause this. All right, by the power invested in me, I hereby hand you in your certificate. Congratulations, Arvin. So we have Avinash. Yeah. Yes. And wait, I think that on deck we have Binash.
How do I use this?
Yes, Binod Batarai, whose remote is on deck.
Yeah, let me know when I'm going to start.
Okay, let's see. Everything working?
Yeah.
Perfect. All right, take it away.
Yeah. A very good afternoon, everyone. I'm Avinash Chaturvedi, a third-year PhD student at the European Southern Observatory in Garching, Germany. First, I would like to thank the CCA Pre Doc program organizers for having me this opportunity to work and learn here. And then my special thanks to my supervisors, Stephanie Tonneson and Greg Bryan, for supervising me on this project. So for my CCA remote pre-doc program, I studied the distribution of atomic hydrogen in TNG 50 galaxy clusters. So let's get started that why I'm interested in learning about the atomic hydrogen in TNG 50 galaxy clusters. First with the background. Hydrogen is one of the most abundant elements in the universe, and neutral atomic hydrogen, or simply H1, can act as a key in exploring the galaxy evolution. H1 is loosely bounded and is observable on a different physical scales for a galaxy in a galaxy cluster environment. And this makes H1 very sensitive tool or very sensitive in the different environmental process which can affect the growth of galaxy in a galaxy cluster. For example, if you look at the H1 distribution on different scales, then starting from this first plot, here is the H1 contour shown around the low mass galaxy NGC 1427 on an ISM scale. And then as we go further on the circumgalactic scale, then here the H1 clouds are shown in the green color, which are around the vicinity of NGC 1316, which is a massive galaxy. And here the H1 clouds are distributed around 100 kiloparsecs. And as we go further in the intergalactic medium scale, then here the H1 clouds are shown in the blue color, which belong to a galaxy NGC 3193, which is a part of a galaxy group known as SVG 44. And here the H1 clouds are within 300 kiloparsec around this galaxy. And this kind of distribution of H1 makes it very interesting tool to probe the role of environment on the galaxy evolution. And in this scenario, some of the most interesting points are what is the origin of the cold gas in the CGM, like whether it's ram pressure stripping or Tyler interaction, and how much cold gas is there in the circumgalactic medium, how the cold gas is interacting and surviving in the hot intracluster medium. And usually to solve this kind of questions or to look at these points, there is a joint approach of simulation and observation, with the requirements that in simulation, we need high gas mass resolution for the ICM or circumgalactic medium. At the same time, in observations, since cold gas is diffuse, so it's need higher sensitivity in the column density, like going down to 10 to the power 19. Luckily, with the technological advancement, we are at the point that where we can achieve these requirements. In simulation, we have TNG 50, which is the last and final run of illustrious TNG. It is a cosmological simulation that runs in a 50 megaparsec box size, providing a gas mass resolution of 10 to the power 4 solar mass. Although it's a cosmological simulation, but with the gas mass resolution of this much, it works like a zoom-in simulation. And at the same time, in the observation, we have an upcoming radio telescope, MIRCAT radio telescope, which provides a column density low to 10 to the power 19, with a spatial resolution of 1 to 10 kiloparsec. And these two things motivated us to study that how much cold gas is there in circumgalactic medium or intergalactic medium. What kind of circumgalactic medium? This comes from the MIRCAT radio telescope. So MIRCAT is currently observing Fornax galaxy cluster. Here you see the beautiful image of the Fornax galaxy cluster showing it within the 1 square degree. And my PhD is about the dynamical modeling of Fornax galaxy cluster. There in that plot, you see the MIRCAT pointings over the Fornax cluster over an area of 12 square degree. So basically summarizing our goal of the project is to study the distribution of H1 in Fornax-like galaxy cluster in the TNG50. And when I say distribution, I mean with the covering fraction of H1 in the TNG50 and make it more like a prediction study that what MIRCAT radio telescope will predict or observe for the Fornax galaxy cluster. And this brings me to methodology of my talk. I started by looking Fornax-like galaxy cluster in the TNG50 and started with a mass cut in the range of 10 to the power 13.5 to 14. And this gave me around 7 halo. And this is how the atomic hydrogen mass map looks like for some of the halo. So here what you see is like out of the 7 halo, there are 3 halos. And what I'm showing you is the atomic hydrogen map color-coded with the column density. And the different circles marks the Vira radii at 0.5, 1 Vira radii, and 1.5. And I'm going to use these maps to study the H1 distribution in terms of covering fraction and specifically in the intracluster region. So before I go on the results section, let me just briefly tell you that how I obtained these kind of atomic hydrogen map. So for getting the column density, I first need the atomic hydrogen mass for each of the gas particles. So for each FOF, I have the gas mass particles, and then I need to remove, for getting the atomic hydrogen mass, we adopted the catalog coming from the study of Gago et al., which is a metallicity-based approach for removing the molecular hydrogen, and then we are just left with the atomic hydrogen mass for each gas particle. And then we have atomic hydrogen mass, then we can do the derived or calculate the column density. And this is done from the just simple calculation like this. So I have the gas particles of each FOF. I bin them in the rectangular grid side of some pixel scale. Here, this plot is just for the visualization purpose, that how I'm calculating the column density. There I adopted a pixel scale of 100 kiloparsec in the rectangular grid. And then for each pixels, I know the gas particles. Then I can get the total H1 mass in that particular pixel, dividing it by the mass of hydrogen atom and the pixel area. This gives me the column density. Of course, when I go for the MIRCAT radio telescope setup, then I use a pixel scale of few kiloparsec. So, and this brings me to the result section of my talk. So here you see the zoom in picture of one of the halo. Remember that the middle circle is the 1 Vira radii, and we are mostly interested in a column density in between 19 and 20, which is the optimal setup of the MIRCAT radio telescope. And this is how the covering fraction of this FOF looks, this halo looks like. So here on the y-axis is the H1 covering fraction. With the covering fraction, I meant in what region of a given area we can observe the atomic gas, H1 gas particles, H1 gas, given a column bin density. So here we are, let's focus on the lime green color, which is 10 column density showing for 19. And on the top, you can see the radius normalized with the R virial. So if you notice around 1 Vira radii, for the green curve, we are seeing the covering fraction in between 10 to 20%. On average, this values, when I include all the FOF include for the covering fraction, then this value drops to 10%. But we are mostly interested in the intracluster region. So for doing the covering fraction for the intracluster, I needed to remove the gas particles belonging to each individual galaxies. And for this, I did a simple thing, like first I removed the gas particles belonging to the individual galaxies within 10 times of stellar half mass light radii. And then we are left with the particles or the atomic hydrogen just in the intracluster region. We checked for other stellar half mass light radii as well, but here in the here I have just shown it for 10 times of stellar half mass light radii. You can clearly see that there is a lot of H1 in the intracluster region. Like 1 Vira radii is around 600 kiloparsec for this FOF. And then if you look at the covering fraction for this particular FOF, then it comes around 1 Vira radii with a column density of 19. The green line curve, it shows you around 10%. And then when we take the average of all the FOF, then this value drops around 5%, and the green light color show the scatter of all the 7 FOF. Finally, this brings me to the conclusion of my talk, that this project, we have estimated the H1 covering fraction in Fornex-like galaxy clusters in the TNG50. We predict that the MIRCAT Fornex survey should observe an H1 covering fraction around 10% at the Vira radii. We find that the TNG50 shows a large amount of H1 in the intracluster region. We also find that the H1 extend more than far out to 30 times of stellar half mass light radii. This corresponds to around 300 kiloparsec or even more. And then for the future work of this work, I plan to compare this with the upcoming Meerkat Radio Telescope survey, Meerkat Fornex survey with the observational study, and then a follow-up study that what could be the cause for this large amount of intracluster H1 in TNG50, whether it's accretion or tidal stripping, and then gain insight in the knowledge in the physics of the cold and hot gas interaction. Thank you. And thank you. Thank you for listening to me. Thanks to the Simons Foundation, and especially thanks to Sai Ganeil, who helped me in learning about the TNG50 data setup.
And thank you for your talk, Avinash. Questions? Them?
No, thank you very much for this. So will Meerkat have the resolution to be able to, so like you had a step where you threw out the H1 that was associated with galaxies.
Yeah.
Is Meerkat going to be working in a regime? Like, I'm not exactly sure the distances of the samples you're.
So basically,
will it be able to do that too?
Yeah, because it will observe the whole galaxy cluster, so it should also cover the intracluster regions between the galaxies. Yeah.
I actually meant more about throwing out the gas that was associated. Like, will it be able to know which gas it should ignore because it's bound to a galaxy as opposed to being intercluster gas?
I think that will come from the way we want to calculate after the observations are done. Yeah, thank you.
More questions? Yes, DK.
Very nice talk. Thank you very much. I was just wondering, how much are your results simulation dependent? Because you said you used 7 halos, right, in total?
Yeah.
Is there like some noise to the halos that you selected, or if you use TNG, I don't know, a different one?
So so TNG50 comes in 3 different setups, 1, 2, 3, and one is the one with the highest spatial and mass resolution. And the specific reason just to go for 7.1 was to direct compare it precisely for the Meerkat Fornex survey, because that will be the first. And giving the same mass criteria, it will be like we have little statistics with the 7, it's not that much, but there's still like with the TNG50, this was the reason to go for this setup similar to the Fornex survey.
So if I understand, so did you look at the resolution study when you did the SIM analysis, but in different resolution simulations?
No, we just
okay.
I just
took
used
the highest resolution and okay.
Yeah, since it has the highest, basically like TNG50, like in the pixel, in the spatial scale, this also provides kiloparsec, and Meerkat Fornex survey will also go for a spatial resolution of 1 to 10. This was the reason to use the.
Yeah, it makes sense that this is the more adapt one.
Yes.
I think that there's value maybe in looking at resolution study, even going to low resolution to see if your results will change substantially, and maybe they do because you're so far away from the resolution you need that maybe it doesn't make sense. But
yeah.
Yeah. Okay. Yeah, Adrian.
Thanks for that talk, Avinash.
Yeah.
In the simulations, what's the fate of this gas? Is it all just heated up and that's it, or does any of it form stars? Or
so in TNG50, like if you ask about these intracluster gas,
yeah,
then it's a part of the future work to explore. But I know that TNG50 has a lower limit in the cold gas, so all the gas particles, they have a minimum, or the lower value is 4,000 Kelvin. So that's the limit for the TNG50. Yeah. So it's limited on that value. But how this is generated, or the temperature, another part is part of future work. Yeah. Thank you.
Okay. Let's thank Avinash again. Now the moment you've been waiting for.
Yeah.
Your certificate of completion. Here
Thank you.
Congratulations.
Thank you.
All right, so we have Binod, who's remote.
Hi, everyone. Good afternoon. My name is Binod Vatrai. I'm currently a graduate student at UC Merced. I recently completed my third year. First of all, I'd like to thank Flatiron and CCA for providing me this opportunity to present at the Pre Doc Symposium today. And I'll also like to thank my mentors at CCA, Dr. Melissa Ness and Emily Cunningham, and also my advisor at UC Merced, Dr. Sarah Lohman, for their mentorship throughout this project. The title of my talk is Intra and Intercluster Metallicity Dispersion in Fire Open Clusters. By intra, we refer to the metallicity dispersion within individual open clusters, and by intercluster metallicity dispersion, we refer to the metallicity dispersion that is between different open clusters. Open clusters are a group of stars that are bound together and remain roughly gravitationally bound for some moment in time. Here I have an example image of the Pleiades open cluster that has roughly 1,000 stars of age roughly 100 million years, and that spans 13 parsecs. Open clusters are considered the building blocks of the disk. They dissolve quickly as within 100 million years of time, and they also disperse in the disk and contribute to the current shape of the disk that we see in the Milky Way. One of the key problems that I'm interested in is can we trace stars back to birth open clusters using chemistry alone? So this process is known as strong chemical tagging, and it has been the key motivating factor behind many popular surveys like GALA. And I'm trying to investigate how unique is the chemistry of open clusters to see if we really can trace stars back to their birth open clusters using chemistry alone. So I'm using fire simulations to investigate the efficacy of such process, strong chemical tagging. So I'll see how unique is the chemistry of open clusters in fire and give some insight on how useful chemical tagging could be. The simulations I use are the lattice suite of fire test simulations. These are the realistic Milky Way-like simulations where we can study star formation and the ISM in a fully cosmological context. It has 9 Milky Way mass galaxies and 3 local group pairs with a mass resolution of 7,100 solar mass. And it has an adaptive spatial resolution of roughly 1 parsec for the gas, and we have temporal resolution of 1 to 2 million years. As FIRE stands for feedback in realistic environment, FIRE also incorporates feedback from solar winds, supernovae, and stellar radiation as well. So with these simulations in hand, I identify open clusters in our lattice simulations. So here I'm showing a top-down view of one moment in time in the lattice simulation. We can see the cold gas in the background, and these colored dots are representing the open clusters that we identified at this moment in time. So to identify star clusters in fire, we use friends of friends algorithm. We set a fixed linking length and choose a minimum number of particles to select a group of stars, and we call them simulated star clusters in our simulations. Here you are seeing individual colored dots. However, there are many stars very close to them, as this is the first moment in time when they were identified. So here I'm showing the iron distribution in a top-down view of one of the lattice simulation. In the background, I'm showing the iron distribution for the young stars that are less than 1 gigayear-old. We can see that in the center, there is high iron abundance, and as it gradually decreases as we move outward the disk, which reflects, which is similar to what we expect for spherical galaxies like ours. And these contours are representing the spiral arms, and these circles that I were plotted here are the open clusters that I've identified at this moment in time. And those open clusters are also color-coded in terms of their mean metallicity. So we can see that based on where the clusters are formed, they have their own their own signatures of chemistry. So I'm trying to see how unique is the chemical fingerprint of these lattice star clusters, so that that chemistry can be leveraged for reconstructing them. So I ran a comparison of the metallicity dispersion of one of our star cluster sample with the star cluster with the dispersion calculated for observation. On the left, we are looking at a star cluster from Apogee that had 28 stars. And in the CN, we're looking at the 60th percentile confidence values of the dispersions calculated in all of these elements by Bovee 2016 work. And in the blue, we're looking at the dispersion with 50th percentile confidence, and the black are the most likely values. So I have highlighted this region in the black to show that the dispersions we have calculated for our 9 elemental abundances in 5 open clusters also fall within the similar range, and they're pretty much small. So this was for one open cluster to show that, okay, our open clusters are also quite similar with what you see in the observations. The dispersion in our open clusters are also quite similar with what you see in the observations. So what about the scatter inside many clusters? So I increased our sample to 361 open clusters in Latte by selecting open clusters towards the by selecting open clusters in the last 100 million years in the simulation. So with those 361 open clusters, I calculated the average dispersion in these 9 elements, and that are shown in the upper panel with these blue lines and the dots. And in the lower panel, I'm showing the same information, but also with red, I'm showing the dispersion around average dispersion for all of these open clusters. So what we can see from here is that in most of the open clusters, dispersion in each element is pretty small. So that is indicating that inside open clusters, stars are quite similar. There is not much dispersion in metallicities. However, I was interested in looking at where these clusters are located in the disk and what their average mean metallicity looks like. And here, the plot on the left, I'm showing the average FU&H distribution with the birth radius of all of those samples of open clusters that we had. And if you look until the first 6 kiloparsec region, there is a clear trend on average FU&H. As you move outward in the disk, the average mean metallicity for these clusters is decreasing. But after that 6 kiloparsec region in the disk, there is a lot of scatter in the calculated average FU&H distribution. So it's also indicating that you can find an open cluster at different radii after 6 kpc having similar mean metallicity. As you can see, I have created a small blue band here that's indicating the region that is plus minus 1 sigma from the overall mean metallicity of all of these clusters. So there are many clusters that fall along that, and they span radii from 6, 8, 10. They're everywhere in the disk, but share similar mean metallicity. To further confirm these results, I selected a sample of clusters from this blue region and looked at the individual metallicity distribution of the stars in those clusters. So all of these colored curves you are seeing here are the metallicity distribution for different clusters that I selected from that blue sample. And these clusters belong to different ranges in the disk. So some as inward as 5 kiloparsecs to some as outward as 14 kiloparsecs. So they are everywhere. They fall in different places in the disk. However, they seem to have almost similar mean metallicity within plus minus 1 sigma. And what's important to note here is that even though they have similar mean metallicity, their individual distribution of metallicity is quite different, as all of these curves have different shapes. So this is kind of telling us that mean metallicity may not be enough to determine birth origin after 6 kiloparsec in the disk. And it is possible to find same mean metallicity, but different formation location in the disk for open clusters. To further investigate the chemical similarity of stars inside open clusters, we used a metric called chemical difference metric, just like in Nest et al. 2018 work. So what we do is we create pairs of stars and find the square differences in their elemental abundances for all the 9 elements and add them, and we call it a metric. So at first, we created all possible star pairs from within same open clusters. So those pairs belong to an individual open cluster. And I did that for a same group of stars that I've shown previously in the blue line, which is plus minus 1 sigma from the overall mean metallicity that was observed for my sample of open clusters. So I created star pairs within open clusters and calculated their difference metric. And I also did a random draw of star pairs, but this time not from the same open cluster, but those two stars belong to two different star clusters, but again from the same sample. So and I plotted the histogram of the metric for these different kinds of star pairs. So in blue, we are looking at the star pairs from within the clusters, and on red, we are looking at the random unique star pairs. So let's talk in more detail about what we see in this histogram. So let's focus on this tall blue bar here. So this tall blue bar belongs to the star pairs within from open clusters, and it has a very small chemical difference as we see here. And almost slightly less than 50% of the cluster populations have that chemical difference. So if we look at the chemical difference of any two stars in the sample, and we find the chemical difference to be that small, then it's safe to say that, okay, these two pairs are coming from a cluster. However, if you go to the next smallest value in the histogram, there is a huge contribution from random unique star pairs in that chemical difference metric. And if you go to the another smallest value in the histogram, there is even higher mixing from random unique star pairs. So that's kind of telling us that there is less than 50% chance for us to tell if any two given star pairs are coming from a same cluster or they are coming from two different open clusters based on their chemical difference alone. So this is kind of leading us to a direction that maybe we cannot use chemical difference to determine birth origin. So now I'd like to leave you with my key summary and work in progress. So we saw that metallicity dispersion in 5 open clusters is small and comparable to observations. Open clusters with similar metallicities can be found across the disk. And the key takeaway is that our ability to trace stars back to birth open clusters using chemistry alone is questionable, and it has large implications for the key motivation behind popular surveys like GALA. And currently, I'm working on comparing these results with other fire simulations. And I'm also comparing this difference metric with apogee open clusters. And one way we are thinking of extending this work is to incorporate the apogee errors in elemental abundances into our simulations and see how our results change. Thank you. And now I'll take questions.
Thanks, Vinod. Time for questions. Yes, Craig.
Thanks. That was very nice talk. What were you able to look at different mass open clusters, like maybe divide the sample into high mass and low mass open clusters and see if they behave differently?
We haven't done that sampling yet. I think that sounds like a good idea. So do you expect results to change based on the mass of these open clusters?
Well, I was going to ask you that question.
Yes. We haven't looked at that, so but I think that would be interesting to see. Yeah. Thank you.
Vinod, so it seems like your result showing that chemical tagging, it's hard to use to determine the origin of stars. Have you thought about what kind of extra information could be useful to add? I guess dynamics will be probably useful things, but is there any trajectory in this project where you're thinking about adding more data to find out a way to do that hybrid chemical tagging to determine the origin location of stars?
Yeah, thank you for the question. So yeah, in this work, we wanted to look at the chemical similarity and to give an insight on whether or not we can use chemistry for chemical tagging. But yeah, so that's part of my thesis. I'm thinking about attempting a reconstruction of open clusters in fire simulations. So one of the ways, like we had initially thought about, is using chemistry and their phase space information. But with our results leading to a different direction, we haven't yet, I don't have a concrete plan on how I'm going to attempt a reconstruction of open clusters. I think that's fair to say that.
Okay, great. No, thank you. And thanks again for your talk.
Thank you.
Just want to say that your certificate is not here, which I believe it means that it's on its way to you. So with that, just want to congratulate you for having gone through the program and having completed the pre-doc program at CCA. And thanks again for your talk.
Thank you.
So now we have Brent Tan, and this is going to be the last talk before the break. So Brent, it's your control. Check if it works. All right. Perfect. Take it away.
All right. Hi, everyone. I'm Brentan. I'm a graduate student at UC Santa Barbara. And the project I've been working on here with Drummond, Greg, and Yanfei is looking at cold gas clouds in galactic winds. And so what are galactic winds? Imagine you have a galaxy right here in the center. So it turns out that the galaxy is interacting with all this gas around it. And so there's a lot of things happening here, but what you just need to know is that there are outflows and inflows that transport the cold gas in and out. And really a good analogy for this is the water cycle on Earth. So on Earth, we have many different processes that bring the water up into the atmosphere and then brings it back down. And this is pretty much the same thing that's happening in the galaxy. Right, and today I really want to just focus specifically on the outflows. And so the poster child for these outflows is MED2, and so we observe these like multi-phase cold winds being blown out of galaxies. Right? And so the question is, if we want to study this using simulations to understand how these outflows work, what do we need to do? And it turns out we need to resolve a whole bunch of scales. And a lot of work has been done on this over the past 5 years. And so let's start at like the smaller scales that we might need to think about. And so these are the mixing layers between the two phases. And this is where the cold and the hot gas is going to mix and interact. And we call this turbulent radiative mixing layers. And I've done lots of work on this. But moving up in terms of scale, if we want to consider clouds, then there's a lot of complexity that comes from having to even if we can model this surface interactions, there's a lot more complexity in modeling the cloud itself. And these are like single clouds in just a wind tunnel, and it's also very idealized. And then we have this big, large scale simulations of a full galaxy. And so this is a MED2-like galaxy with, and you can see this multi-phase outflows from the top and the bottom. And so all the white stuff there is cold dense gas. And what we want to do now is to bridge this small scale idealized simulations with this large scale wind simulations. And that's where our simulation falls in between these two scales. And we really want to be able to go from the cloud to the disk scale and then from the disk scale to the wind scale. So what's the picture we're trying to get at here? The questions we want to ask is, how do the clouds form? How are they seeded? And then how do they evolve? So how is the clouds changing with time? Are they growing? Are they getting destroyed? And how are they interacting? So how are they interacting with each other, and how are they interacting with the wind itself? And are they back reacting on the wind? What's the mass, momentum, energy transfer between the two phases? And today I'm not going to answer all these questions, but I'm going to show like what's the setup to like probe these issues. So this is our simulation setup. We have the disk, and we're not going to simulate the whole galaxy, so we're just going to take a patch. And so this gray box here is our simulation box. So these are known as like tall box simulations. We can see why. But because we want to not just look at the breakout of the wind, we want to study the clouds. We want to follow the clouds in the wind for some distance. And so we make our box even taller on one side. And so we are running this in Athena++, and the dimensions of our simulation are 500 parsecs on the short side and 2 kiloparsecs on the long And we're aiming, so we have a resolution of 1 parsec. So that's pretty good. Boundary conditions, periodic on the side and outflowing on the top and the bottom, as you might expect. And we include like a whole bunch of physics. So we have gravity, which creates a stratified medium, and so we have our 10 to the 4 disk material in the disk plane. And then we drive turbulence in the disk. We also have magnetic fields, and we include radiative cooling. So that creates your multi-phase ISM, which is going to be our initial conditions. And I would like to add that we have this very nice algorithm for cooling and heating. And so if you're interested in that, we can chat after that. Also, PSA, we motivate this simulation. We managed to use this to convince SCC to enable parallel I/O. So if you run large simulations, you can now write out your output in parallel. So our simulation is going to progress in this fashion. And so we start on the left, we have our multi-phase ISM disk. We imagine there's a star cluster in the center. And the stars in this star cluster are going to explode after some time. And so we inject energy and mass. And this is going to create a hot super bubble in the center. And eventually this super bubble is going to break out the disk. Once that happens, it's going to drive this hot outflow. It's going to launch the wind, and the disk material that you break up along the way is going to seed the clouds for the wind. And so this creates this nice multi-phase outflows on the top and bottom. So what does this look like? We have temperature, outflow velocity, density, pressure, and magnetic fields. And you can see that the supernova, the hot bubble broke out, and we have this nice wind, hot wind. And if you look on the left, you can see all these small clouds entering in the wind. It's just nice to look at. All right, so some things I want to highlight about this simulation. Firstly is that the winds are very turbulent. And this is important because it's what you really do not capture in the smaller idealized simulations of single clouds. We have X, Y, and Z velocities. And you can see that the wind itself has turbulence on the order of the outflow velocity. And that's really going to change the environment that the cloud's evolving in. And we can also look at horizontal slices. So these are just cuts at different heights. And so from left to right, it's going in increasing height. And you can see that if you just look at it face on, you can see all these small clouds in the wind. But if we take each slice and we just plot temperature versus velocity for each slice, we can see as a function of height how the velocities in the different phases are changing. And so in the top region, so temperature is on the y-axis. So the top region is your hot gas, and the middle region is where all your cold cloud material is. And you can see that as you increase in height, the velocity difference between the hot wind and the cold gas basically goes away. And that's really indicating that the clouds are getting entrained in the wind. So we can also see spatially where all the different phases of our gas is located. So the very cold gas, which is like 100 kelvins, is only at the midplane, which is what you would expect. The cool 10 to the 4 gas, it's in the ISM, and it's also what forms our clouds. And then the clouds are basically just this hot volume filling hot wind. And then you have this 10 to the 5 gas, intermediate temperatures, which is basically at the mixing layers of these clouds. So we can look for what's the mass flux as a function of height for the different phases. And you can see, so the blue line to the right side is really where the wind is. And the blue line is the net total mass flux. The green line is the mass flux of the hot gas, and the red line is the mass flux of the cold clouds. And you can see that the cold clouds and the hot gas roughly contribute equally to the mass flux. But we also want to focus on the cooler stuff, which is the clouds. And this is one of these like text to image generation models that's like all the rage now. And so I put in clouds in the galactic river, and that's what I got on the right, and I pretty good actually. So to identify single clouds, basically what we can do is we just apply a threshold. And so we are doing it at 10 to the 5, which is where the intermediate gas is. And so everything below 10 to the 5, we consider it cloud material. And of course, you remove anything touching the boundary and near the disk, and on the right side is what you end up with. So that's the cloud mask, basically. And so anything that's connected and in the mask belongs to the same cloud. And so we label each cloud with a different color. You can see on the left this confetti looking like image, where each color is a different cloud. And we can do the simplest thing we can do is just what's the distribution of the cloud sizes, right? We also can check is this affected by our choice of this threshold. And the choice of the threshold doesn't really matter. Doesn't change the distribution much, except at the very small cloud sizes where we are not resolving the clouds properly. And so delta X is our resolution. You might notice it's at 2 and not 1, but that's because the high resolution run is still running. So this is actually from the lower resolution run. But the rest of the clouds follows this nice power law where you have an equal amount of mass in each power bin, basically. And this was seen in like turbulent box simulations also. So completely randomly, I chose the 9th biggest cloud, and we can calculate properties of that one cloud itself. So it's a 30 parsec cloud. It's moving at like 50 kilometers a second, and it has a magnetic pressure support of 20%. And we can also see what the 3D structure of the cloud is. So here's like the Lego version of the cloud, where it's like just rendering the voxels. And we can do a better job with matching fields, and we can see like the surface mesh of the cloud. So the wind is coming in from the left here, but what's interesting here is like this tendril like structures coming out of the cloud. But why stop at one cloud when we can do many clouds? And what I want to highlight here is that the clouds are morphologically very diverse. It's very different from this head-tail structure that you see in the wind tunnel simulations. And that's again because of the turbulence. And you might notice all these small clouds around the larger clouds. That's because we're rendering the bounding box. My advisor likes to call them the TIE fighters, the mothership. And so just to end off, the next steps there's a lot of analysis left to be done. We want to compare to like existing models, how like those simpler ones, and how we can refine and extend like analytical models, and hopefully like have a good subgrid prescription for larger scale winds. Thank you. That's all.
Thanks, Brent. Time for questions. Yes, Stephanie.
This was great. Thank you very much. So when you had your distribution of cloud sizes, was that over? I missed what period of time in the simulation is.
Right. So that was for a single snapshot that I was showing, but I've actually looked at the time evolution of that, which is also interesting.
Yeah, that's actually my question. What is that?
Yeah. So basically, when the wind breaks out, it very quickly forms this power law, and then it stays in this power law right until as long as your wind is being driven, you see that power law. It's quite steady, and then it of course it falls off once the wind gets shut off. But it's actually quite a time steady like distribution.
That's really interesting. Thank you.
Yeah.
Brent, can you go back to the slide where you're showing the mass flux as function of depth for the different phases?
Yeah.
Yeah.
Oh, this?
Just
this one.
is one. Yeah. So I guess that may be expected, but this seems to suggest that there is maybe even like a different spectrum of scale for the different phases. And have you looked at that spectrum? And what I mean by that is that the hot medium, well, moving faster, but also seems to have like a much smoother mass flux as function of height compared to the cooler distributions.
Right. I mean, that's really because the hot gas is volume filling, whereas the cold gas is concentrated in the clouds, and so there's a lot more stochastic motion. But so if you look at the time evolution, yeah, well, I mean, it's just varying around a smooth line also, but.
More questions? Okay. If not, thank again, Brent, and your certificate of completion. Thank you so much. Congratulations.
Okay, welcome back. From one Italian to the other. I think this is the first time I meet most of you. I'm Simon, I'm part of the CCA, but I'm sitting in the opposite building in David Spergel's group. So you probably haven't seen my face that much. But I'm part of the CCA and I'm a cosmologist. And as Chris said at the beginning, I was part of the committee that selected you guys for this. And I'm really, really impressed with the work that you've done. So amazing job. And now Matteo is taking my spot for that committee, and I'm sure will do even a better job than me. So I'm excited for what has to come also for this program and the connection that you guys will have with the CCA now and also in the future with the prospective pre-docs that will come here. And I'm sure they have a lot of questions for you. So just to say, if anyone reaches out to you, please let them know about your experience, and they might have a ton of questions as you might have at the beginning. So we're trying to improve that part as well. So from now to 4:30, we'll have 6 more people, I believe. Lee Kivenson is the next one. Please make your way here. And I will keep your time, 15 minutes, 10 plus 5. I'll try not to bother too much. Thank you so much.
Okay, thank you very much. And thank you for having me. Yeah, my name is Lieke van Son. I'm a graduate student at the CFA, and I'm going to talk about some of my results with that I did as part of the gravitational wave group here. So I'd also very much like to thank them for hosting me. And so I'm going to be talking about the neutron star black hole mass gap, but in light of gravitational wave observations. So you might think, why do this in terms of gravitational wave observations? Well, as I hope most of you know, we've seen an incredible increase in the number of gravitational wave detections over the past 7 years or so, since the start of gravitational wave astronomy in 2015. Because the first catalog that we got from 2 emerging binary black holes only contained 3 events. This catalog more than doubled in O2, more than doubled in O3A, until we were left here in November with about 100 detections of both binary black hole mergers, black hole neutron star mergers, and binary neutron star mergers in gravitational wave transient catalog 3, GWTC3. Oh, yes. So there's a lot of information here, and this really drives the main question of my PhD thesis. What can we learn from all these merging double compact objects about the massive stars that precede them? And how can we use this information to learn something about the universe? But now that we have about 100 detections, we can also already start to ask ourselves, have we learned something so far? And so I want to share what my favorite lesson from the third gravitational wave catalog is. There are features in the mass distribution of merging binary black holes. So if you plot out the primary masses of black holes, so the more massive component of binary mass black holes, against their rates,
then you see that a single parallel really doesn't fit. We have some bumps and features and parallels and shapes, and understanding these features and where they come from have all kinds of implications for understanding how these merging binary black holes are formed. But even if we really understand them and their redshift evolution, they might help us break the degeneracy between observed masses and redshifts, which will allow us to do some cosmology with these features. So it's really fundamental that we understand these features and peaks. And so there's a lot of information in the whole distribution. I only have 10 minutes. So I'm only going to focus on one feature that is, I think, is not talked about enough, and that's the low mass feature in this distribution. So let's zoom in. What do I mean when I say the low mass feature? Well, it appears that the binary black hole mass distribution peaks globally at about 9 solar masses. That might not sound super interesting, but 9 solar masses is actually kind of surprising if you think of the IMF, because the initial mass function favors the progenitors of 3 solar mass black holes over the progenitors of 8 solar mass black holes by about an order of magnitude. So I would argue that we cannot investigate this peak of the black hole mass distribution without also understanding why there is a dearth of lower mass black holes. And I think the right question to ask here is, where are the black holes with masses between 3 and 6 solar masses? Now, this might start to sound very familiar to a lot of you, but I want to be very agnostic. And so I think there's really only 3 options. The first option is we just don't see them. This means that these black holes exist, they merge, but our detectors miss them. And so there's some kind of observational bias against detecting these systems. Now, even though this is in some form maybe true, we kind of understand our bias. And this question is going to be answered more concretely with future detection surveys as we get more and more and more data. So for the purpose of this talk, I'm just going to assume for now that these features are real and there is really a peak at 9 and a drop below. Then only 2 options remain. Either these black holes don't exist, so we never form black holes with masses between 3 and 6 solar masses. And what I mean here is, and this is what is known as the classical neutron star black hole mass gap. This was actually proposed about a decade ago to try and explain seemingly missing black holes in X-ray binaries, where there also seemed to be a lack of low mass black holes. But since then, there have been more and more detections of black holes with masses in this mass gap. And so it seems that if there is a gap, or if and this was based on a theory saying that maybe the supernova remnant mass function is discontinuous. And so supernovae just don't form black holes with masses between 3 and 6 solar masses. But there seems to be some evidence against this. It's unclear and not completely resolved at this time, but at least if there is really a gap, it shouldn't be completely empty. But there's a third option, and that's this last option. Maybe black holes with masses between 3 and 6 solar masses exist, but they just don't merge. And this is what I would call an evolutionary bias. So this is not too weird of a thing to think about, because if you think of all the systems that form gravitational wave events, they're only a very, 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 very small subset of all stars that exist and go through a supernovae. So the question then becomes, so this could be a telltale of the formation channel of these black holes. So the question then becomes, is there a formation channel that predicts such a dearth of low mass black holes? And many, many different channels have been proposed to form merging binary black holes. But at this low mass end, which is why I like low mass end of the distribution so much, only a few formation channels expect to have a global peak at this lower end. Now, I specifically work on isolated binaries, so I focus mostly on these 2 channels in my day-to-day work. And so the isolated binary pathway towards merging binary black holes can be subdivided broadly in 2 big groups. One group being all systems that experience unstable mass transfer or a common envelope at some point, which is the common envelope channel. And one set of systems is all those systems that never experience unstable mass transfer, and so only stable mass transfer, which I will call the stable mass transfer channel. These channels have different predictions because they lose angular momentum in different ways, and they lead to different final masses and systems. And I'm going to talk or focus only on the stable channel today. So what do we expect to see from the stable mass transfer channel? Well, that's exactly what I show here. So what I did is I ran a population synthesis model called COMPASS to simulate a population of merging binary black holes at the local universe. And in gray is now the band from the gravitational wave transient catalog 3. And in pink, I overplot what we fiducially expect from the stable mass transfer channel. Not only does the rate match up locally, but it also seems to have this steep drop and peak that fits the most recent predictions. But you should never just trust your simulations unless you understand why your simulation is doing something. So it's exactly what we set out to do, is understand why does the stable mass transfer channel show this drop and dearth of low mass black holes. And so in order to answer this question, what I did is just bring back the stable mass transfer channel to its core kind of key evolutionary phases in an almost cartoonish way. And what we found is that requiring the second mass transfer phase in this evolutionary channel to be stable imposes a minimum mass on the allowed black hole masses that you can form with this channel. And so I'm not going to bore you with the derivation because I don't have time for it, but actually we can translate this requirement or this boundary of stable mass transfer into an analytical formula that predicts what the minimum allowed black hole mass is based on only 4 physics parameters, uncertain physics parameters, such as the core mass fraction, the critical mass ratio for stability, etc., and one initial distribution value, namely the initial mass ratio. And so this is all really fun and nice, but that's just an analytical formulation. Does it actually match what our data suggests? So in order to show you that, here I'm plotting the output of a population synthesis model with the more massive component mass on the y-axis and the SAMS mass ratio on the x-axis. And you already see that the gray dots, which is the population synthesis model, shows this clear minimum cut. And this is what our analytical prediction predicts the minimum to be. So it's not a fit, but it does predict the minimum pretty well. So here I'm quantifying this a little bit by drawing triangles over the location of the 99th percentile, so where 99% of the simulation has a mass higher of this value. And then we can repeat this exercise by doing this for a whole bunch of physics variations that we've just seen or that we think are the main physics parameters that cause this minimum relationship. So here, every color is a different simulation, is a different variation. In this case of the core mass fraction, the triangles are the simulation and the lines are the analytical prediction. And you can see that our prediction does a pretty good job at predicting or explaining what we see in the data. You can translate this back into a mass distribution that we would observe with LIGO Virgo at low redshifts. And you see that depending if you have a higher minimum here, so the dark brown line, you get a higher minimum in the mass distribution, and so you get a dearth of low mass black holes without needing to apply or implement a supernova remnant mass function with a gap. We did the same for mass transfer stability variations and mass accretions variations, so just the amount of mass accreted during the first mass transfer phase. And we see it in all variations. We kind of know what's going on and we can explain features in the mass distribution. So what this shows is, or the main summary of my talk is, the stable mass transfer channel towards merging binary black holes has this key characteristic feature of predicting a minimum black hole mass, minimum primary black hole mass. And this can cause a dearth of low mass black holes in a gravitational wave inferred mass distribution that would look like the neutron star black hole mass gap. And that is everything. So I'd like to take questions. Thank you very much.
Just wanted to mention, if you are at home on Zoom and you have a question, raise your hand. I'll be able to see it. Otherwise, from the room, any question?
I think that's super interesting. So this is only, as you pointed out, like this is only one of the channels that binaries can go through. So does this also then like place a limit on how important some of these other channels are, or?
Yes, yeah, 100%. So actually the common envelope channel I've at the moment purposefully excluded because it complicates the story a lot. But the common envelope channel doesn't naturally produce such a dearth of low mass black holes. And so at the moment, the common envelope channel is for most people still the prevalent, like dominant channel forming merging binary black holes. It's definitely needed to form merging neutron star, but for more massive black holes, it's not so certain. And so what would be a smoking gun is if we detect a lot of black holes with masses in the gap through Gaia, etc., or through other mechanisms, but we still observe a dearth or a drop at about 9 solar masses in the gravitational wave distribution, then we could maybe say, okay, maybe this stable channel is really the dominant one at this low mass end, which is not currently what most people think.
Okay, we have time for one more question. Please go ahead.
Interesting. But I mean, the other thing is that when you do have mass transfer through this mode, like there are also other frequently observational consequences.
Yeah.
Right. It's easier to pick out than like common envelope evolution. So I'm kind of like, are there other constraints that you think will gradually be built up that would inform this?
Yeah, so one of the things that people immediately think of is the X-ray binary consequence of this, because these systems should go through 2 phases of X-ray bright accretion modes. And so, yeah, ideally you would like to compare those to the rate of X-ray binaries throughout the universe, but it's hard to do that directly because these most likely come from a completely different epoch in the universe. So yeah. Exactly. But there's hope. I mean, there's different supernovae and other kinds of constraints. Ideally, we would like to use everything at the same time. Now I very much focused on the masses, but mass ratios and other things like that would also help greatly in trying to reduce which formation channels can form where. But again, the low mass end is, I think, really key, that this is one of the few points where you have only a few channels that can create a global peak. And so these also have different predictions, making it a lot more easier to kind of finally filter out which ones could be true or not.
Okay, let's thank Liki again.
Next up is Manami.
Hi, everyone. I'm Manami Roy. I'm a 4th-year graduate student at Raman Research Institute. Here, I'm working with Kangi, Stephanie, and Drummond. First of all, a big shout out for them for being such amazing mentors. So the goal of my project is to study how satellite galaxies would affect the cooling of the host galaxy's circumgalactic medium. So the circumgalactic medium is a region in between the galactic disk and intergalactic medium, which is filled with very diffuse gas. So my mental picture of CGM or circumgalactic medium is a cupboard of not so very organized person like me. So if we look at the cupboard from the outside, we could see that it's a quite organized thing. But if we open the door of the cupboard, we can see the real mess. So similar is the CGM. So you might think because of its diffuse nature, it's a very quiet place, not much thing is going on there, but it's not the case. If we zoom in and focus on the small details, we can see the real mess. Like there is outflow, inflow, recycling gas, and whatnot. And these are the process which makes and maintains a very multi-phase CGM. Multi-phase mean it has a very wide range of temperature from very hot phase of 10 to the power 6 Kelvin to very cool phase of 10 to the power 4 Kelvin. So now in the cosmological simulation, we could see this wide range of temperature distribution and also a lot of this cold gas out there in the CGM. Whereas in the idealized simulation, we don't see these amount of coal gas out there in the CGM. So what is happening here? What are the missing links between the idealized simulation and the cosmological simulation? So the idealized simulation takes into account these processes like outflow, recycle of gas, inflow, whereas in the cosmological simulation, there is two additional processes which can contribute to coal gas to the CGM. One is accretion of gas from intergalactic medium, and second is accretion of gas from the satellite galaxy. We would focus on how satellite galaxy contribute this cold gas to the CGM of the host galaxy. So for this, we did a very controlled experiment where we used some idealized simulation where we consider the mass of the host galaxy to be a Milky Way type, which has a component like black hole, stellar bulge, stellar disk, gas disk, dark matter halo, and CGM. Whereas for the satellite distribution, we explored different mass range from very small satellites of 10 to the power 8 solar mass to very massive satellite of 10 to the power 10 solar mass. Satellite has all the components like the host galaxy except for the CGM. So now let's see. So these are two 10 to the power 10 satellites, one at 150 kiloparsec and another at 100 kiloparsec. And they're orbiting around the host galaxy in a circular orbit. And you could see there are lots of cold gas is coming from this satellite galaxy. Oh, yes. So now we could see in this movie that there are lots of coal gas coming from the satellite galaxy. Now let's see what are the processes by which the satellite galaxy would contribute the coal gas to the CGM. So let's zoom into the region around the satellite galaxy and see what is happening there. So this is the zoomed in version of the satellite galaxy where the triangle means satellite gas, circle means host gas. If we see the blue color, that means it's a cool gas. If we see the red color, that means it's a very hot gas. So one process is ramp pressure stripping. So when a satellite galaxy moves through the CGM of a host galaxy, then it experiences a drag or a pressure, which is known as ramp pressure. And if this pressure dominates the gravitational pull of the satellite galaxy, then it can strip the gas from the satellite galaxy. Apart from ramp pressure stripping, there are other ways by which a satellite can induce cooling in the CGM of the host galaxy. First of all, mixing layer cooling. So if the coal gas is stripped from the satellite, it tries to mix with the hot host gas. And then in the mixing layer, the temperature is like that, which is very susceptible to cooling. So basically there would be cooling in that mixing layer. Second of all, it's a turbulence driven cooling. So if a satellite passes through the CGM of a host galaxy, it would start the CGM and it would create some local instability, which would also drive cooling. So mixing layer cooling and turbulence driven cooling these two cooling are happening outside of the satellite, but because of the satellite. Whereas, last of all, there can be cooling where the hot host gas could fall into the satellite and gets cooled. So now let's see whether we could see these different origins in our simulation. So now in this movie, you could see that there are not only there are lots of stripped coal gas, there are also a lot of mixing layer cooling is happening around the satellite. So let me play the movie. So the cross are black holes of these two satellites of 10 to the power 10 solar mass, where the red points are the stripped satellite coal gas, and the cyan point overlapping with the blue are the induced cooling, which is happening outside of the satellite. And you could see that those cyan points with blue almost overlapping every time with the red point, that is with the stripped satellite coal gas. That means they're mostly coming from the mixing layer cooling around this stripped cold gas from the satellite. And just getting inside the host galaxy. So now let's see what is the time evolution of this stripped cold gas. So these three color denotes three different satellite distribution, one of 2 satellites of 10 to the power 10 solar mass and 20 satellites of 10 to the power 9 solar mass, and also the 200 satellites of 10 to the power 8 solar mass. This is to just keep the total mass of the satellite distribution to be constant. So what is similarity between among these three curves are like the stripped gas increases over time and then they reaches a peak and then they decreases. So for this plot, we made a radial cut of 40 kiloparsec to exclude the ISM of the host galaxy. So what are the differences between these three curves? So you can see, whereas the massive galaxy continues to feed cold gas to the CGM till 4 gigayear, the less massive one of 10 to the power 8 solar mass are losing their stripped gas very fast, like within 1 to 1.5 gigayear. So what is actually happening to these gas? Are they falling into the host ISM as we have seen in the movie, or they are getting mixed with the hot gas of the host CGM? So let's see what are the temperature evolution of these cold stripped gas after they get stripped. So for 10 to the power 10 solar mass satellites, this is the distribution of the temperature evolution after they get stripped. So you could see that there is a peak in the 10 to the power 4 Kelvin. So that means most of the gas, most of the cold gas are remaining cold. We can see that also in the CDF, where you could see that 70% of those gas are remaining cold. So this dashed line implies the cold gas below which we consider it to be cold. Now, for the 10 to the power 9 solar mass satellite, we could see that there are two peaks almost getting similar, like 10 to the power 6 peak and 10 to the power 4 peak. That means 50% of cold stripped gas are remaining cold and 50% of the cold stripped gas are getting mixed with the hot CGM and gets heat up. And we could also see that in the CDF. Whereas, amazingly, at 10 to the power 8 solar mass satellite, you could see there are no peak at 10 to the power 4K. Like most of the cold stripped gas are getting mixed with the host CGM and getting heated. And that is also very clear from the CDF. So, which is expected because the clouds, the cold clouds from the 10 to the power 10 solar mass satellites are large and they remain cool. They retain their temperature, whereas for the 10 to the power 8 solar mass case, they are small satellites and their clouds are very small and they tends to get mixed and heat up. So now we have an idea how the stripped satellite gas evolved with time. Now let's see how the satellite would induce cooling, like how the induced cool gas mass evolve with time. So from this two curves, so you could see the upper panel is, so the upper panel is the total induced cool gas mass, and the lower panel is the gas which induced cool outside of the satellite. That means either they're coming from the mixing layer cooling or they're coming from the turbulence driven cooling. So from this two plot, you could see that those are on similar order of magnitude. That means basically satellite induce similar amount of cooling in the CGM of a host galaxy like the stripped cold gas. From these two curves, you could see they are also in similar order of magnitude. That means most induced cooling is happening outside of the satellite. And from these two curves, you could see that these two curves almost mimic the shape of each other. So this induced cooling basically mimics the shape of the stripped cool gas mass, but with a delay time. That means they're somehow correlated. And that means most of the induced cooling is coming from the position of the satellite galaxy. That means the position of the stripped cold gas and from the mixing layer. So basically, most of the induced cooling is coming from the mixing layer around the stripped coal gas. So now the take-home point is, yes, that's it is confirmed that satellite can produce a lot of cooling in the CGM of the host galaxy, and by ram pressure stripping and by induced cooling, and those two are actually in the similar amount, like similar amount of induced cooling like the stripped gas. Second of all, is like the most of the induced cooling is happening in the mixing layer of the stripped coal gas. And last but not least important, which is like coal stripped gas from the less massive satellites are small, so they are likely to get heat up and get mixed with the CGM. But whereas from the most massive galaxies, the most of the clouds are larger, so they retain their temperature. So thank you so much. I would like to have questions.
Questions for Manami? Check Zoom 2. Yes, sorry.
Thanks, that was a really great talk. So I'm trying to connect this in my mind to the Milky Way. And so we have Sagittarius, the dwarf galaxy, which is roughly in your upper mass bin. It was probably accreted a long time ago, but it probably came in with a significant amount of gas. Do you think there would be any residual structure in the gas around the Milky Way that would be affected by Sagittarius?
Yeah, we could see a lot of clouds. We could detect a lot of clouds there because of the large satellites. And our plan is to also to do a realistic distribution of satellites around Milky Way to see that whether we could find those structures and we could see like anything which is observable.
Cool. Yeah, it'd be interesting to see how long they persist.
Yeah,
well.
yeah.
Cool. Thanks.
I don't know if this
Yeah,
is
you're good.
okay. It's working. So I was just interested on, maybe I missed how these satellites are spatially distributed.
So for 10 to the power 10 solar mass satellite, one at 100 kiloparsec, another at 150 kiloparsec from the center of the galaxy. And for 10 to the power 9, it's randomly distributed in between 100 to 150 kiloparsec, whereas for 10 to the power 8 is also the same. It's a randomly distributed because there are a lot of more satellites, 220 satellites. So they are randomly distributed.
Thank you.
Let's see if we have one more question. Yes.
This is kind of secondary to the physics that you were looking at, but I think I found it very interesting the degree to which that material was actually coming into the main disk of the galaxy, kind of like a rain, right? It wasn't the sort of picture of gaseous satellite accretion where the whole thing comes in a bolus. like what you're actually getting is that, you know, having this thing merging through your halo is just sort of producing this. So I think it'll be really interesting. And also because of the cooling, you are getting more gas onto the galaxy than you would think just from accretion. So I think it'll be, you know, it might be interesting in the future to kind of look at, you know, are the detectable imprints or changes in the disk star formation response to this, because I think it's, you know, it's often been an interesting question about how do galaxies sustain star formation for longer periods of time, especially if the accretion's impulsive. But here, this is something where you're changing some of the time. I don't know. I think it's an interesting thread to pull on.
Okay, let's thank Manami again. Thank you so much.
Next up is Mike.
Oh, hello, everyone. I'm Mike. I'm a PhD student at Monash University in Melbourne, Australia. And my usual interests are in interactions between stars in binaries and multiples, and in binary evolution, particularly common envelope evolution. But today I'll be talking about something quite different. That's what I've been doing here at the CCA for the past several months on the simulating planetary engulfment. And so that's what's being shown in that picture here, when a planet gets eaten up by its host star that it orbits. My main collaborators are Matteo Candiello and Adam Germain at the CCA, and I'm also working with Morgan McLeod, Rio Hirai, Ilya Mandel, and Daniel Price. So let's begin with looking at the demographics of planets. So this is a distribution of exoplanets from the NASA Exoplanet Archive as a function of the planet mass on the vertical axis and the orbital period in the horizontal axis. And immediately we can see that there are some subclusters. We have these objects that are about Jupiter mass divided into the hot Jupiters and some cold gas giants here at larger periods. And in the lower mass range, we have this cluster here, which are the mini Neptunes and super Earths. So we know that about 1% of sun-like stars host hot Jupiters, and these are, and that's this subcluster here, which have periods of less than a few days or separations of about 10 to the minus 2 to 0.1 astronomical units. However, we also know that stars expand significantly after their main sequence evolution. And so they are expected to engulf any hot Jupiter companions that they would have. For example, if all of these planets are orbiting around sun-like stars, we know that our sun is expected to reach a maximum size of about an astronomical unit when it turns into a red giant. And so that means all these stars here will become engulfed and become star food. And besides that, is there any evidence so far that planetary engulfment actually takes place? Well, I present here two slightly puzzling pieces of observations that might be possible signatures of planetary engulfment. So the first one is the observations of chemically enriched giant stars, and particularly lithium-rich giants. So we expect giant stars to be depleted in lithium because lithium gets burnt out via proton fusion, starting from the pre-main sequence. And also these stars, their surface abundance gets significantly diluted on the giant branch due to the first dredge up that mixes in lithium depleted material from the stellar interior onto the surface. However, we actually find that 1% of giant stars are lithium enriched, and even lithium super rich, meaning their surface lithium abundance exceeds the meteoritic abundance. And this could possibly be explained by pollution from an engulfed hot Jupiter, which are objects that are too cool to, well, not high temperature enough to burn lithium, but they're also cool. And another piece of puzzling piece of observation is the observations of rapidly rotating giant stars. We generally expect giant stars to be more slowly rotating because as objects expand significantly, their rotation slows, just like an ice skater that's spinning around would slow down as they extend their arms. And so planetary engulfment can possibly spin up a host giant star
by depositing the orbital angular momentum of that planet into the star. And so to study whether planetary engulfment is a viable explanation for these observations, there are several scientific questions that we could possibly investigate. Firstly, if a planet is engulfed, where in the envelope will it be destroyed? And how much material is deposited in the giant star's convective envelope? Because only there will material be mixed up onto the surface and be seen. And to study rotation, we could also look at how efficiently is a star spun up by an engulfed planet. So I am here tackling these questions, hopefully, by performing hydro simulations of this process. So this is our setup. There are three components to the setup: the star, the planet, and their mutual orbits. So for the star, we're using a 1 solar mass star that's evolved to the giant branch, red giant branch, up to a radius of 4 solar radii. So that's the Hertzsprung-Russell diagram, the evolution of the star there. And we obtain the stellar structure of this star using the Mesa stellar evolution code. And the thing to note about the structure of the star, it's illustrated on this diagram on the right here. It has a deep convective envelope that's more than 90% of the stellar radius, and a very tiny but dense helium core that's less than 1% of the stellar radius. And onto modeling the planet itself, we're modeling that as a Jupiter-like object, a gas sphere. So it's mass of about 1,000 times that of the sun, radius 1/10 of the sun. And we model that as an n equals 3/2 polytrope. So past studies have actually mainly modeled the planet as a point mass, but that's problematic because point masses only experience gravity, whereas here in this regime, hydrodynamical drag is actually important in depositing the orbital energy of the planet into the envelope. And also, we wish to study the mass loss of the planet, the mass ablation of the planet. And so we cannot study that self-consistently if we model the planet as a point mass. And for the initial orbits, we assume that the orbits of the planet around the star is circular and Keplerian, with the planet just touching the stellar surface. And we perform our hydro simulations with a smooth particle hydrodynamics code, or SPH code, called Phantom. So this is a movie of our simulation. We're now looking at a density slice in the orbital plane of the simulation. This big disk here is a star, a smaller disk around it, the hot Jupiter to be engulfed. So I'll just let this movie play. And here, the planet goes inside the star, reaches the very deep interior because it loses orbital energy dissipated by the hydrodynamical drag. The trajectory of the planet can be seen by plotting a separation time curve like this. So we start at 4 solar radii, that's about the size of the star, and the planet goes down all the way and stops at about 0.1 solar radii or so. And here I've also labeled the whole engulfment process in several stages that I will briefly describe. So the first phase is that the planet completes multiple orbits near the stellar surface, as you've seen in that movie, without going in by that much. That's the region highlighted here, which we call the grazing phase. And at some point, the planet starts to inspiral significantly. It becomes fully engulfed, and the rates of inspiral is comparable with the orbital period itself. And this is the main engulfment phase. And the dissipation mechanism in both the grazing and engulfment phases is hydrodynamical drag. The only difference being that in the grazing phase, since only part of the planet is immersed in the stellar envelope, the effective cross-section of this that the drag acts on is reduced. And we also have a sinking phase here. Here, the planet trajectory becomes mainly radial after some time. And that's because the drag force that it experiences is so strong that it dissipates away all its orbital angular momentum. And so it more or less sinks radially. This can also be seen more clearly if we look at just the planet's trajectory in the movie. So I've hidden the star in that movie over here, just showing the planet. So there's several interesting things here. At the end, the planet undergoes a very radial path, and also we see these nice Kelvin-Helmholtz instabilities. And what's the final fate of the planet? Well, at some point, the planet becomes tidally disrupted by the dense stellar core. This occurs when the average density inside the interior to the planet exceeds some average density of the planet. But however, this is quite different from a usual tidal disruption because the planet is in a radial orbit. So in a usual tidal disruption, a star, for example, gets stretched by a supermassive black hole into a nice thin arc. But here, the planet really only elongates along its radial direction because it's traveling along the direction of gravity or the direction of the tides. And finally, this tidally disrupted planetary material settles at some fixed point in the end. And that's actually when the planet, when this material becomes neutrally buoyant. It's literally floating right there in the star. And that occurs when the density of this material is in equilibrium with the density of its surrounding material in the stellar envelope. And here's one main result. It's showing the mass ablation of this planet. So we have on the vertical axis, the mass of the planet, and on the horizontal axis, its separation from the stellar center. So the evolution of the planet is such that we go from right to left in time because it inspirals. And we can see that actually the mass gradually goes down as a function of separation. And so we observe in the simulations that our planet, that mass ablation occurs gradually, and it actually deposits over 90% of the mass into the convective envelope of the star, which is shaded in this diagram. And that's quite in contrast to past studies that a lot of them have have assumed that the planet doesn't really lose mass until it becomes tidally disrupted or is disrupted by a strong ram pressure. So I'll summarize our investigation here. Most planets are expected to be engulfed by their host stars, and planetary engulfment could be possibly explain a range of puzzling observations, including chemically enriched stars and rapidly rotating giants. So we simulated this process, the engulfment of a hot Jupiter by a red giant star, and we find that 90% of the planet's mass is gradually ablated over the engulfment process. And perhaps, therefore, planetary engulfment might be a viable explanation for chemically enriched giant stars. Thank you.
Questions?
Hi, Mike. This is great. So I was wondering about the criterion that you take for the tidal disruption of the planet. You just compare the average density of the planet to the average density of the gas that it has in its surrounding, which I guess in your simulation is allowed to evolve, though, right? The gas density as the planet spirals in. How robust is that criterion? Like, and how much is the change of the density at that location due to the in-spiral of the planet?
Right. So maybe as you can see from the simulation, the movie itself, you can see that the star is barely disturbed by the entry of the planet, and that's because of the really strong mass ratio. The planet's 1,000 times lighter than the star, so it doesn't really disturb the structure inside. And moreover, the planet goes in over almost the main engulfment occurs in less than an orbital period, so it doesn't go through the same parts that it has already disturbed, even by a little bit. And so the density structure of the star doesn't really change from the initial unperturbed structure. And to answer the second part of the question, we therefore believe that our criterion for where the tidal disruption occurs is relatively robust.
And I think there was, okay, yeah, go first.
gravitational pull from the stars that you know how sometimes you can detect like the radial velocity detection of planets. I wonder if there's some sort of signature that you can observationally tell whether a planet may be. Then I'm thinking about the 90% mass loss. It may be.
My main thought is that the problem with a direct observation of the active engulfment is that it's such a short phase. It's occurring on the dynamical time of the star, in this case, several days. And so it's going to be really hard to catch such an event.
One last question.
Really cool work, Mike. I really like it. So you talk mostly about the planet actually depositing mass into the envelope, but I was also really interested in the spin part that you mentioned. So did you actually find any significant spin up, and do you expect then also the envelope to be coupled to the core? So do you actually think the core would even be able to spin up as well?
So about the first part of the question, in the simulation itself, the deposition of the planetary material throughout the envelope is quite inhomogeneous at the end of our simulations. So it's actually quite hard to observe any coherent spin that's induced in the whole star. But we did estimate that an upper limit to the amount of spin it could induce just by using conservation of angular momentum would result in spins of about 10 kilometers per second, so in the whole star. As for whether this spin has any implications, how it's related to the spin of the core, I don't really know. But to get a significant spin up, I think we need to use larger planets, maybe brown dwarfs or the larger mass tail of the hot Jupiters.
Okay, let's thank Mike again.
Thank you.
Next up is Paco.
So I'm Paco Holguin, and over the last year and a half, I was working with Chris Hayward, somewhat informally, and so I'm very happy to be finally able to present my work here at the CCA. And I actually just graduated with my PhD at the University of Michigan earlier this month, and in about a week and a half, I'll be starting at the Applied Physics Lab in DC. They're in the DC area. But I'm very excited to talk about the contribution of stars to the ionizing field of the CGM. So, of course, very common, very useful figure. You know, in galaxy evolution, there's a lot of processes that are shaping the galaxy, and the CGM happens to be right at the center of it. So it's being shaped by all these processes. So it's very important to study the CGM. And it's very challenging to study a CGM for many reasons. And one of the reasons I want to talk about is the role of the ionizing radiation field. The ionizing radiation field influences a lot of the diagnostics that you might use to detect or determine the state of the gas in the CGM. And it also plays an important role in determining, for example, neutral hydrogen fraction. And so modeling the stellar radiation field is challenging because it's not, the stars are not just at the center of the galaxy and a point source. They're embedded in a three-dimensional structure, and there's a three-dimensional gas structure that we've seen in many of the presentations previously. And radio transfer is very hard. And so that's the question I want to answer just very broadly is, can we tell what the extent of the ionizing radiation field from the stars is? And also, how does this answer change with halo mass and redshift? So to start, we can just do some analytical work to get a sense of, what we might expect for this type of question. And so what we can do is just simply say that the radiation field from the stars is going to depend on the photon injection at the galaxy. 1 over r squared dilution, and then apply some escape fraction that sort of about 0.1. And then we set that equal to the metagalactic field, and then we can solve for this transition radius. Now we can do some quick calculations connecting the photons to the star formation rate. They should be proportional. And then we can do star formation rate to stellar mass to halo mass. And suddenly we can plot the transition radius as a function of the redshift halo mass parameter space. And so here in this plot, in red, I'm just showing the star formation rate as a sanity check. So you don't have to focus on that, but what you can focus on are the black contours and the filled contours, which show the same information. But what we can see here is that here's the 0.2 contour. So transition radius is about 0.2 of the virial radius. And so for the most part in this parameter space, the stellar contribution extends up to 0.2 of the virial radius, maybe less if you get down to here. So Milky Way is right here. And as you get to higher redshift, the transition radius we'd expect actually gets to significant fractions of the virial radius. We can keep this in mind when we do further work on this. Because of course, real galaxies are not this simple radial picture. And so what I'm going to use are just 12 halos from the FIRE2 simulations, which of course have an extensive set of feedback models that create really realistic galaxies. Now, so the FIRE2 contains an approximation to give radiative effects in the simulation, but it doesn't include sort of more sophisticated radiative transfer you might want to use. And so we have to post-process these simulations. And so what I'm doing here is I'm going to post-process the snapshots in these halos. And I'm going to be using a Monte Carlo radiative transfer code that was used by Zhengqing Ma to study reionization galaxies. And so I'm using it for lower redshift galaxies. But I'm going to run this twice. So first, I'm going to run this for all the sources, the stars in the background field. Then I'm also going to run it with the stellar sources suppressed. And so we get two estimates for the ionization rate around different parts of the galaxy. And there's a lot of choices that we can actually make in what this transition radius would be. It's not as clean as in the analytical case where we can just set two two profiles equal to each other and just solve. And so, I'll just mention these two examples, but I really only talk about one of them. So what we can do first is tag which stars have been affected by stellar radiation. And we can do this by just simply taking the ratio of these two of the ionization rate that I mentioned earlier from the two estimates. So if I turned off the stars and the stellar radiation and the ionization rate didn't change that much, then that cell must have not been affected by stars. Let's say by a factor of, it doesn't change by like a factor of 2. And so through that criteria, we can tag a star as stellar affected. And then one way we can define the transition radius is just by counting, at what radius have we enclosed 90% of the mass that is in stellar affected cells. And so here I'm showing a profile of the mass for the stellar affected cells, but it's relative to the profile of mass of all of the cells. And so, as you get farther out into the galaxy, it starts decreasing, and 90% enclosed stellar mass is right here. So this is just an example of one snapshot from a high redshift galaxy. That's why the virial radius is really small. So we can see that, roughly we're below 10% of the mass contained at this radius. And so definitely by this radius, which in this case is close to 20 kiloparsecs in this galaxy, by this radius, we really shouldn't, outside of that radius, you shouldn't be expecting much
stellar contribution. And so it kind of forms an upper limit. You can also look at just take the mass profiles. So just take the mass profiles of the two Monte-Carlo transfer runs, and so we can see, both of them. The black is all ionizing sources, and the red is the stellar sources are suppressed. As you get to higher radiuses, they match to the metagalactic value, but as you get closer to the galaxy, they diverge, as expected. And so where they diverge can also be a transition radius. So I'll just compare the upper limit measurement that I mentioned for time purposes. And so, back to this analytic case, we remember that we had about 0.2 in sort of intermediate redshift and mass. Now, if we look at the results over here, of course, galaxies don't uniformly fill this space, so there's a lot of gaps and it's not uniformly filled. But just pay attention to this contour right here, 0.2. Here's a 0.1 contour, and here's a 0.5 contour. So what's different here is that it seems that for low redshift galaxies, pretty much mass independent in this for the masses that I tested here, we really don't care too much about the stellar sources out into the CGM. So below 0.2, 0.1 VO radius. But as we get to higher redshift, suddenly you do care about it even up to 0.5 of the virial radius. And so there's a lot of differences in how we might compare these two situations. So the star formation rate in the simulations is actually less than what I assumed in this analytical estimate. So that's one reason why it could be suppressed, at least at these higher redshifts. But that's not the that's not the whole question. That's not the full picture. So before I go through my summary, I also want to mention we can look at the fraction of data points in a particular bin that exceed a particular transition radius. And so yellow means greater than 50%. That is most of the data points in the bin. And blue is less than 10%, so not significant amount of data points. And because I'm running out of time, I'll just say, as we get to 0.2, the difference between 0.2 VO radius and 0.5 VO radius, suddenly we go from most of the data points in all these higher redshift bins being above 0.2 to now only the highest redshift have significant amount of data points that are above that transition radius. And so, so I mentioned some of these conclusions, but what I want to just end on is further work on this, of course, is going to need a lot more in-depth investigation that we just set out, Chris and I, to answer the broad question. As we sort of did this work, we found out that there's a lot of details that need to be accounted for, especially since the propagation of photons is going to depend not just on the star formation rate, but the porosity of the medium, the mean density of the medium, and that is a very rich system. So thank you.
Questions? Okay. If not, thank you so much, Pablo. Congratulations. Next up, I missed the name, is Pierre. Thank you.
For waiting. Hi, everybody. I'm Pierre. Pierre Fedorowicz. I'm a graduate student from the University of Arizona. And so, still waiting. There we go. So the past 2 semesters, I've been working on a project with collaborators here at the Flatiron Institute, as well as at the University of Arizona. a new method for using generative adversarial networks to generate fast full sky weak lensing simulations. So let's start off by talking about weak lensing. So weak lensing is one of the key cosmological probes that we have in all modern photometric surveys. These include surveys like DES, HSC, KIDS, LSST, just to name a few. And the general idea here is that gravity due to mass along the line of sight causes light to be bent, and that bending of light, if you're looking at, say, a source galaxy in the background, ever so slightly distorts the image of that galaxy. And so those ever so slight distortions are what we call weak lensing. And by measuring those distortions, we can actually work out what the mass distribution of the universe looks like. And the key here is that these weak lensing measurements are sensitive not only to luminous matter, but dark matter as well. Just to give you something nice to look at, this is what the density field would look like reconstructed from these weak lensing observations for a simulated DES year 1 like survey. Okay, so we know that nonlinear structure growth causes the matter density field to become highly non-Gaussian, particularly at small scales. And so the optimal method for extracting that non-Gaussian information is actually by forward modeling the full nonlinear density field. And so previous work has shown that by doing this forward modeling based approach, you can actually improve cosmological constraints by up to 5 times compared to more traditional summary statistic based methods. And so, however, the problem here is that the big obstacle is that you need to be able to run simulations as a part of that forward modeling step. And so just as a point of reference, the DES cosmology chains required something on the order of 300,000 likelihood evaluations. If you needed to run an n-body simulation at every single one of those likelihood evaluations, that would require something like 20,000 CPU years. That's clearly computationally intractable. And so really being able to deliver on this promise of these field-based inference methods requires that we can create a fast forward model that's accurate enough to approximate these simulations. So there have been previous machine learning based methods for doing so. One of them, for example, here, this is the most relevant and recent work in this field using generative adversarial networks. This is you et al. This year, took a very traditional GAN-based approach. And so here, what we're starting with is we start with some low-dimensional Gaussian noise vector. This is our input or our latent space. That's in this case, it was a 584-dimensional latent vector that then passes through a generator, which is a very flexible neural network with 5 million parameters. And the output there is the mass map or the density field. And in this case, that covered the KIDS 1000 footprint, or approximately 75,000 pixels. Finally, that goes through the discriminator, which is also another neural network, which has its own 5 million trainable parameters. And both the generator and discriminator are trained through the adversarial loss. And one of the key things to note here, or actually 2 key things, is the input dimensionality does not match the output dimensionality, right? So we have 584 degrees of freedom in the input space, but the output space has 75,000 degrees of freedom. And on top of this, the generator has to learn all of the physics across all physical scales. That's quite a large task. So our approach is slightly different. Instead, we decide to use the log normal model to generate an initial approximate density field. We know that the log normal model is accurate on large and intermediate scales. However, it fails at small scales. And so if you were to look at the statistical properties of the mass distribution between n-body simulations and the log normal at these scales, it would be incorrect. And really the failure of that log normal model at those scales is due to inexact local physics. And so what we want the generator to do is to be able to recover that missing physics that the log normal model doesn't get right. And it must do so through a local mass redistribution. And so in our case, what we're doing is we're using GAN training convolutional neural networks to locally redistribute that mass such that the log normal model or the log normal input map is perturbed such that it has the accurate or that it accurately approximates those n-body simulations. And so we can go back to the outline of the more traditional approach, and really what we're trying to do here is trying to modify what's highlighted here in red. So we can take a look at what our generative process looks like. We start off by sampling just a white noise map. This is, just a Gaussian noise vector, but it has the key here is that this has the same dimensionality as our output maps. So this covers the full sky. In this case, it's around 3 million pixels. And so what we're really doing here is we're making sure that the input latent space has the exact same number of degrees of freedom as the output space. We then take that input noise vector, run it through the log normal model, and that generates our initial log normal field that has those correct large and intermediate scale physics, but the incorrect small scale physics. And finally, we pass that through the GAN. The GAN performs this local mass redistribution, and this is a very small neural network. It's fully convolutional, and on top of that, it's rotation equivariant. The underlying physics of the universe is a rotation equivariant, and so we impose that the model that we're learning for that missing physics must also be rotation equivariant. As I said, it's a very small model. Because we're only trying to learn that small scale physics, we don't need to learn the physics of every scale of the universe. We can actually restrict it quite significantly. Here we only have 3,000 trainable parameters as opposed to the 5 million trainable parameters of the other approach. On top of that, we only have a receptive field size around 1 square degree. And you can see, that little circle in red is roughly about the size of that. So what that is the generator cannot see features larger than that scale. And I mentioned, we're only trying to learn these small scale physics. Because of that, we can actually we can train on like 3.5 by 3.5 degree patches rather than the full sky. So it makes training faster, and you also don't need all the world's memory on the GPU. Okay, so for training and testing our simulations, we use these, or for training and testing our network, we use these suite of 108 simulations generated for the HSC survey. These are full sky weak lensing simulations, all at the same fixed cosmology. We use 80 of these for training. And because we're splitting these up into 3.5 by 3.5 degree patches, we actually get 240,000 training patches out of that. And then a further 28 simulations are kept for testing. So after we've trained our generator, we can use it to actually start generating full sky weak lensing maps. And so I won't tell you which is which, but one of these hemispheres is an n-body simulation, and the other is one of the simulations generated by our GAN. You can also see some zoom ins on those two hemispheres as well. And what you'll find is, just staring at it forever, that you really cannot distinguish by eye the statistical properties of the two. So indeed, in this case, the northern hemisphere here is the GAN, and the southern hemisphere is the n-body simulation. For a more quantitative comparison, we can look at a number of statistical properties of each map. The first one we're looking at here is the power spectrum. In blue is these n-body simulations, and in orange are the GAN-generated maps. And we can see that we recover the power spectrum to within around 1% error. We can next look at the 1-point function. And we're also now showing in green the log normal model. We can see the log normal clearly fails to capture the correct 1-point function. But once again, the GAN is now perturbing those log normal maps in the right direction such that we're again achieving around 1% error on the 1-point function. We can also take a look at these higher order peak and void count statistics. And for those, we're achieving a few percent error. So it looks like I'm starting to run a little low on time. So I'm going to leave this up but I'll quickly summarize by saying what we have is, we've created a model that is extremely fast. We're able to run about 10,000 times, generate a full sky simulation about 10,000 times faster than using n-body simulations. On top of that, to my knowledge, we're the first to come up with a full sky generative weak lensing model. And at the end of the day, our model is statistically indistinguishable from those n-body simulations at the accuracy required for modern photometric redshift surveys. So thank you. Any questions?
Thank you. Okay, we have full 5 minutes. Any question?
Yep. Thanks for that talk. It's super cool. This is way too technical, and I'm just throwing it out there because no one else raised their hand. But because you stick with small patches, your network doesn't have to understand anything about spherical geometry. Is that true?
So we are training on the curved sky. So the network is actually implemented such that you're performing convolutions over a fixed map.
Okay, got it.
So we don't train on flat sky. These are not traditional Euclidean convolutional neural networks.
Cool. Thanks.
Any other question? I agree on the very technical, but very cool too. Okay, if not, let's thank Pierre again. Thank you so much. Congratulations. Last talk from Sophia.
Awesome. Hi, I'm Sophia Lilleangen, and I stand between you and drinks. Sorry for that. Okay, also while we're waiting. So I'm also like a final year grad student at Surrey right now, and last week of the pre-doc program here. And I've been working with Adrian and Catherine here and Anna Bonazza. And hope you can read this. So I'll tell you a bit about deforming dark matter halos, stellar streams, and information theory. And I found this on the literature walk, like between the station and the library walk. Information is light, information in itself about anything is light, which I thought was quite cool. Okay, let's start. This is the Milky Way, and we see nicely, so this is in the middle, we see the disk, which is Gaia, and then we see on the bottom right the LMC, and the LMC is currently falling in, and it's quite massive, and it is perturbing the Milky Way in several ways. So some stuff we've already observed are that there are overdensities in the stellar disk, and the stellar halo, which we see here in the white circles. There's a reflex motion of the disk, so the disk gets pulled down towards the LMC. And the thing I'm interested in for this project is it induces a dipole in the Milky Way halo. I've talked a bit more about that in last week's lunch talk as well about all these things. So yeah, hope you were there. So how can we probe the dark matter halo? And a really cool thing that we have, but that we can observe in the Milky Way are stellar streams. So here we just see many different streams. Streams are disrupted globular clusters, disrupted accreted globular clusters or dwarf galaxies that are just in the tidal field of the Milky Way, building these filaments. And we have them in very many different shapes, basically, not shapes, but everything else. So we have short ones, long ones, thin and thick. And yeah, each of the streams has a story to tell. And a way of how we can get the story is we model the stream. And with that, we also model the Milky Way. To do that, we need the progenitor, so the galaxy or globular cluster that fell in, where we have, for example, a position of a velocity and some other parameters in the model. And we need the Milky Way halo. That can be very simple or very complicated. Always has like a mass, a scale radius, a shape, and other parameters. So there's been quite a lot of stream modeling done to learn about the Milky Way. But with this project here, we wanted to step a step back and ask the question, what exactly do stellar streams measure, particularly with regard to the dark matter halo? And so I said the LMC induces a dipole. That dipole is time dependent. So what can we learn about this time dependence of the dark matter halo? And then we've seen there are many streams. So which streams do we need? How many of them do we need to get good constraints? And also, we've only seen the track, but there's also kinematic data. So what type of kinematic data do we need? We can try to answer these questions with information theory. So Arvin talked about that earlier already. So now it's applied to streams. So there was a paper by Anna Bonazzo and David Hogg, and our work is based on that, just including those time-dependent potentials. So other examples are the radial velocity measurements for exoplanet search that we had earlier, and also, for example, Fisher forecasting and cosmological parameters. Now, the exact question that we try to answer is, how well do streams constrain the time-dependent dipole of the Milky Way dark matter halo? So I mentioned information theory and information content. What exactly does this tell us? So with information theory, we try to answer, when we have given data and given data quality, how well can we constrain the model uncertainties? What's like the best possible uncertainty on a model parameter that we can get? So the model that we're using, I said, is like the progenitor and the Milky Way halo. And now we introduce a time dependence. So to give in the middle shows you like a time dependent dipole in the halo. We do very simple toy models. So this is just an NFW halo and an external perturbation from a multipole that's described by those alpha, A1 nil, etc. coefficients. So with that stream model, we can make a fiducial stream model. Here I've shown the stream track, but there are other observables such as distance and velocities. And now to come to the fun part is you want to take derivatives of these observations. So with information theory, you can either go via the likelihood and try to understand information from that, but we don't, like our model is a bit too complicated to have a smooth likelihood for that. So we take derivatives of the observable with respect to the parameter. So here's an example from the paper from Bonazzo and Hogg. So in gray, it's like the stream track, and then we vary a model parameter here, the halo mass. We go up and down, and then along each observable, we take the difference in the streams. And that's then in the bottom that we see, that's the derivative of the parameter of the observable given a parameter. With that, we can calculate the Fisher matrix. And the Fisher matrix is the inverse of the Kramer-Rao lower bound. That will then give us like the uncertainties, the best case uncertainties. So here we've seen this equation earlier before. So dy over dx is this derivative object that we see in the middle. And then we have this covariance matrix that's basically the data errors if they're not covariant. And with that, we can get the best case uncertainty on model parameters. In this case, we're mostly interested in those coefficients here. So let's look at some results. So this is very preliminary still. It's like, don't completely trust the numbers or the results that I'm showing yet. We're still developing stuff, but yeah, it's been quite difficult. So now I'm showing you a stream that's run in an NFW halo where we added a static perturbation. So the perturbation we add is a dipole. It's like a magnet we see here. A1 nil, the coefficient is in Z direction. A11 coefficient is in XY direction. That's why it's turning, just to show you the different surfaces. This is the stream we get. So in gray, underlying is now the perturbed potential, and we run a stream model in there. And this is how our result looks like in information theory. So I've shown here, I'm showing here 4 parameters that we've varied. So on the left column is a progenitor parameter, X of the progenitor, just to show this part of the model. In the middle, we see the NFW halo, the mass. And then we have on the right-hand side and the bottom row are the perturbation coefficients. And here I'm exploring what different data dimensions do to the information. So we have some streams where we have beautiful 6D data and we get some uncertainty. Again, don't really trust numbers, but they're roughly percent-ish. Cool. So we have here beautiful full data, but what happens for those many streams where we only have the track? So for quite a few, here I've now only included the track, and for quite a few model parameters for the progenitor and the halo, the uncertainty get a lot bigger. Well, for the perturbation coefficient, so the bottom right plot, it actually doesn't change between 6D and 2D, which could be quite promising, that we only need really the track on the sky to constrain the dipole, which would be super cool. But again, it's preliminary. I don't trust this 100% right now. And just to show you the other way, now we remove the track, which is completely unphysical because without seeing the stars, you can't have other parameters of the stars, but just to show you that then obviously the uncertainty gets bigger. You can also look at different streams on different orbit, how they constrain different parameters. So now we have those three streams. So a planar stream that I showed before in blue, the polar stream in yellow, and OC is a stream. So a stream that's like a real orbit that we can, a stream that's like the orbit or the real stream that we can observe. And it seems like different streams constrain different parameters differently good. So we are going to explore this more, look at more realistic streams or like streams and realistic halos and see what this will bring us. And then finally, now I'm introducing the time dependence. So again, we take the NFW, but now this A1 nil and A11 parameter that we get, we make this dependent of time by introducing a polynomial where we now want to learn about the coefficients of this polynomial function. So A1 nil nil, etc. So this is now how the potential looks like. It's evolving in time. And now I've only looked at one stream. Actually, like here we see two streams. Underneath we see a red stream that we don't see. That's run in just the NFW halo. And then in blue on top, it's run in the NFW plus perturbation halo. So it seems like they look quite similar. The perturbation doesn't do much to them. And now we can have a look at the information in there. So it seems like the information contained in there is also not doesn't vaguely differ. It's interesting in the bottom right what's going on, that a stream that is perturbed can tell you more about the perturbation than a stream that's run in an unperturbed potential. We need to look into this more. And then just to get to my conclusions and the outlook. So stellar streams hold information about the deformation of the Milky Way in the stream track mostly. And we've implemented those perturbation potentials for Gala. So we have the static potential, we have the time-dependent perturbation. So we're gonna put that onto Gala soon and then you can use it as well. And it was also quite difficult to do all this information theory. Like it was very numerical with like all kinds of derivatives and stuff. So fun time to explore that. That also leads into quite, some issues we had. Also like inverting matrices with infinity condition number doesn't work. So a lot of fun. And then in the future, like to finish this project, we want to get like more realistic streams. We want to combine streams to learn about the information. We want to look at different data qualities. We want to fix the issues, obviously, and we want to publish the code and the paper to that. And I want to end with a very, very big thank you to the CCA, to the Simons Foundation, to my mentors, to the Dynamics group, to the other pre-docs, and to everyone else. Like, I had an amazing time. I learned so much. I got so inspired. I met so many cool people. I had really the best time. So thank you very much.
Thank you. Questions?
So I think it might be because the data for the track is so good. But I mean, then you might also have the same constraints for the rest. So I'm not completely sure, but it also it matches my intuition on my other project where I've looked at streams and those deformations and in simulations. And there we also found only an effect on the track. So I'm not sure exactly why. That's something we want to look into once we've confirmed that that's actually true.
Thank you.
More questions? Yeah.
So this is totally new topic to me, but thanks for this great, nice talk. I was curious that I thought that maybe different streams should give the same NFW hello thing because they should be in the same potential, but you thought that they could give the different types of NFW hello, or I missed something.
So what I was talking about is the uncertainty on the mass that you get for the NFW halo.
Okay.
So we want if you run stream models, then you get a mass from that, and we want to say the mass you get has an uncertainty of 5, 10, 20%.
And how large is the uncertainty?
That's what we're trying to infer with those ellipses. Basically, the X or Y axis basically tells you how large the best uncertainty is that you can get.
Okay, thank you.
Yeah, the back.
Really cool. Do you need to have continuous streams? So I know gaps in the streams are really big, really popular things to look into. Can you get more information out of gaps, or do you have to assume that there's none? So
yes and no. So for getting information about the global potential, we tend to ignore the gaps. So what you can do with gaps is really learn about substructure that hit the stream, which is also really cool, dark matter subhalos or other substructure. There's other modeling techniques for that, and I guess you can also do an information theory project on those models, but we so far ignore those.
And I think we have time for one more question, if there is any. Okay, let's thank Sophia again. Congratulations.